Take a deep breath. Go ahead. Fill your lungs with air. Feel your chest expand. Feel that familiar sensation of breathing that you've done about 20,000 times today without even thinking about it. That breath you just took, it travelled through 60 miles of atmosphere to reach you. 60 miles of invisible ocean pressing down on your skin right now with 14.7 pounds of force on every square inch of your body. You can't see it. You can't taste it. You barely notice it. But it's there. Always there. That thin blanket of air wrapped around our planet like the most delicate of shields. Tonight, we're going to imagine what would happen if it disappeared, if Earth lost its atmosphere. Hello and welcome to the Sleepy Astronomer. If this is your first time drifting through the cosmos with me, welcome. I'm so glad you're here. And if you've travelled with me before through distant galaxies and dying stars, it's wonderful to have you back for a journey that's perhaps more intimate than any we've taken before, because tonight we're not exploring some distant corner of space. We're exploring the invisible ocean we swim in every moment of our lives. Whether you're settling into bed, curled up in a favourite spot, or perhaps sitting near a window where you can feel a gentle breeze on your skin, I'm so grateful you're here to explore this question with me. If you enjoy these peaceful explorations of the cosmos, I'd be so grateful if you'd subscribe to join us for more cosmic journeys. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through space. Now, before we venture into this thought experiment, let me offer you this comfort. Earth's atmosphere isn't going anywhere. Not tomorrow, not next year, not for billions of years. Our planet has held onto its atmosphere for over 4 billion years, and it will continue to do so for billions more. What we're about to explore is an impossible scenario, a way of making the invisible visible by imagining its absence, a way of appreciating the gift we never think about until we consider what life would be like without it. It's safe here. You're breathing right now. The air is still there, and it will be there when you wake up tomorrow morning. But here's what makes this question so powerful. When you imagine losing something you've never consciously valued, you suddenly see it clearly for the first time. When you walk through what would happen if the atmosphere vanished, the silence, the cold, the impossible harshness of an airless world, you begin to understand the daily miracle of simply being able to breathe. And perhaps most remarkably, you realize how rare this is. Most planets don't have breathable atmospheres. Venus has an atmosphere, but it would crush and cook you. Mars has an atmosphere, but it's so thin you'd suffocate in seconds. The gas giants have atmospheres you could never reach through and no surface to stand on if you did. Earth's atmosphere, it's just right. Not too thick, not too thin, not too hot, not too cold. Just perfectly, wonderfully, almost impossibly balanced for life. Tonight, we'll explore what our atmosphere actually does for us, all those invisible services it provides every second of every day. We'll walk through what would happen if it disappeared, from the first impossible seconds to the hours and days that would follow. We'll see what Earth would become. We'll look at Mars as a warning, a planet that lost most of its atmosphere billions of years ago and became a frozen desert as a result. And perhaps most importantly, we'll learn to appreciate something we take completely for granted: the ocean of air above you, the breath in your lungs, the blue sky you saw today, or will see tomorrow, the protection from radiation and meteors, and the cold of space, the gift of a planet that wrapped itself in exactly the right blanket to keep life warm and safe. So, settle in, take another breath, notice it this time, and let yourself relax into this journey. The question is unsettling. What if Earth lost its atmosphere? The answer? Well, the answer will help you appreciate every breath you take for the rest of your life. So, what exactly is this invisible ocean we're floating in? Let's start with the basics, because the atmosphere is one of those things we think we understand until someone asks us to explain it. It's air, right? Well, yes. But what is air? Air is a mixture. 78% nitrogen, 21% oxygen, and about 1% other gases. Argon, carbon dioxide, water vapour, a few trace elements that hardly register. That oxygen? That's what you're breathing right now. That 21% is keeping you alive, keeping every breath possible. The nitrogen is mostly along for the ride, diluting the oxygen to a concentration that won't burn you from the inside out. Pure oxygen, it turns out, is a bit too enthusiastic for everyday breathing. This mixture extends upward from the surface about 60 miles. Though 60 miles is where we typically say, that's where space begins, there's no sharp boundary. The atmosphere just gradually fades out, getting thinner and thinner, until there's so little of it that we might as well call it space. Most of the atmosphere, about 75% of its total mass, lives in the first 10 miles above the surface. This is the troposphere, the layer we live in, where weather happens, where clouds form, where everything we think of as the sky takes place. Go up in an airplane, cruise at 35,000 feet. That's about 6.5 miles, and you're still in the troposphere, though you're getting close to the top of it. The total mass of all this air, about 5 quadrillion tons. That's a 5 with 15 zeros after it. It sounds like a lot. It is a lot, if you're talking about moving it, or weighing it, or trying to comprehend it. But here's the thing. Earth is a big planet. And compared to the size of Earth, 5 quadrillion tons of atmosphere is actually a pretty thin skin. There's a comparison that gets made often, and it's worth repeating because it's so striking. If Earth were an apple, the atmosphere would be thinner than the peel. Think about that for a moment. That entire 60 miles of air, all 5 quadrillion tons of it, is proportionally thinner than the skin on an apple. We live at the bottom of an ocean that, cosmically speaking, is barely there. But thin as it is, that atmosphere does an extraordinary amount of work on our behalf. First, and most obviously, it gives us something to breathe. That 21% oxygen is continuously replenished by plants and algae through photosynthesis. Every breath you take contains oxygen that was probably produced by a plant sometime in the last few years. You're breathing recycled air in the best possible sense, air that's been through the lungs of countless other organisms, processed by countless plants, cycled through the atmosphere in a pattern that's been going on for billions of years. Second, it creates air pressure. Right now, the atmosphere is pressing down on you with about 14.7 pounds of force per square inch. That's the weight of all that air above you, pulled down by gravity. You don't notice it, because you evolved in it, because your body is built to handle it, because the pressure inside you matches the pressure outside you. But without that external pressure, things would get uncomfortable very quickly. Water boils at lower temperatures when pressure drops. This is why cooking takes longer at high altitudes. At zero pressure, water boils at any temperature, including body temperature. Third, it distributes heat around the planet. Air moves, it circulates. Hot air rises, cold air sinks, and the whole system creates winds and weather patterns that move heat from the equator toward the poles, from sunny areas to shaded areas, from dayside to nightside. Without atmosphere, the temperature where you're standing would depend entirely on whether the sun was shining on you at that exact moment. No evening warmth after sunset, no mild winter days, just Sun equals hot. No sun equals cold. Fourth, it blocks harmful radiation. The ozone layer, that band of O3 molecules in the stratosphere, absorbs most of the ultraviolet radiation from the sun. UV radiation damages DNA. It causes mutations, cancer, cellular breakdown. A little bit of it gives you a tan or a sunburn, depending on your complexion and your common sense about sunscreen. A lot of it would sterilize the surface. The ozone layer has been quietly protecting life on Earth for hundreds of millions of years. Fifth, it burns up meteors. Tons of space debris hit Earth's atmosphere every single day. Most of it is small, dust-sized particles, pebbles, occasionally something larger. When these objects hit the atmosphere at cosmic speeds, many miles per second, the friction with air molecules heats them up until they vaporize. They burn up. Shooting stars, we call them, though they are not stars at all. They're rocks encountering atmosphere and losing that particular argument. Without atmosphere, all those rocks would hit the surface. All of them. Every day. Sixth, it moderates temperature through the greenhouse effect. Certain gases in the atmosphere, water vapor, carbon dioxide, methane, trap heat. Sunlight passes through them easily, hits the surface, warms it up, and the surface radiates that heat back as infrared radiation. The greenhouse gases absorb some of that infrared and re-radiate it, some of it back toward the surface. Without any greenhouse effect at all, Earth's average temperature would be about 0 degrees Fahrenheit instead of about 59 degrees. We'd be a frozen ball. Seventh, it creates weather and climate. Rain, snow, wind, clouds, storms, all of this requires atmosphere. Water evaporates from the oceans, rises into the air, condenses into clouds, falls as precipitation. Weather is just the atmosphere doing what it does. And weather, despite occasionally being inconvenient, is necessary for life. It distributes water across the planet. It erodes rock into soil. Eighth, it carries sound. Sound is vibration traveling through a medium. In air, sound waves are compressions and rarefactions, regions where air molecules are pushed closer together, and regions where they're pulled farther apart. Without atmosphere, there's no medium for sound to travel through. Without atmosphere, the universe is perfectly, utterly silent. And ninth, it makes the sky blue. This is pure physics. No biological necessity involved, but it's beautiful nonetheless. Air molecules scatter sunlight, and they scatter blue wavelengths more efficiently than red wavelengths. This is called Rayleigh scattering. So when you look up at the sky, you're seeing scattered blue light from all directions. At sunset, the light has to travel through more atmosphere to reach you, and by the time it does, most of the blue has been scattered away, leaving the reds and oranges. This is why sunsets are red. It's atmosphere doing art. The atmosphere is structured in layers, each with its own characteristics, each doing its own part in this protective system. The troposphere, as we mentioned, is where we live. Ground level to about 7 miles up, though this varies. It's thinner at the poles, thicker at the equator. This is where weather happens, where temperature generally decreases as you go higher. Above the troposphere is the stratosphere, extending from about 7 miles to about 31 miles up. This is where the ozone layer lives, absorbing UV radiation and, in the process, warming up. Temperature actually increases as you go higher in the stratosphere. It's more stable than the troposphere. No weather up there, no turbulence. Pilots like the stratosphere. Above that is the mesosphere, from about 31 to 53 miles up. Temperature drops again here. This is where meteors burn up, where noctilucent clouds form, those strange, beautiful clouds visible in polar regions during summer, made of ice crystals at the edge of space. Then comes the thermosphere, from about 53 to 375 miles up. Temperatures here can reach thousands of degrees, though temperature is a tricky concept when the air is so thin. This is where the aurora happens, where the International Space Station orbits. And finally, the exosphere, from about 375 miles to maybe 6,000 miles up. This is barely atmosphere at all. This is where atmosphere transitions into space, where the distinction becomes more philosophical than physical. All of these layers, all of this structure, it's held in place by gravity. Earth's gravity pulls air molecules toward the center of the planet, and they pile up at the surface, creating pressure, creating density, creating the conditions we need to live. But here's what's interesting, and a little unsettling if you think about it too long. Gravity is the only thing holding the atmosphere down. There's no shell, no container, no boundary keeping it in place. Just gravity. And if a planet loses its magnetic field, if it's bombarded by solar wind, if conditions change, atmospheres can be lost. We know this because we've seen it happen. Mars had an atmosphere once, a thick one. We can tell from the geology, ancient river valleys, lake beds, deltas where rivers emptied into larger bodies of water. Liquid water requires atmospheric pressure. Mars must have had enough atmosphere to keep water liquid on the surface. It probably had rain, maybe snow, possibly even oceans. But Mars lost its atmosphere. Its magnetic field failed. The core cooled, the dynamo stopped. Without that magnetic shield, solar wind stripped away the air, molecule by molecule, over millions of years. Today, Mars's atmosphere is less than 1% the density of Earth's, mostly carbon dioxide, so thin that liquid water can't exist on the surface. The planet is a frozen desert, and the atmosphere it once had is mostly gone, blown away into space. Earth still has its magnetic field. Our core is still hot, still churning, still generating that protective magnetic bubble that deflects solar wind. As long as that continues, and it should for billions of years, our atmosphere is safe. But it's worth knowing that atmospheres can be lost, that this protective blanket we take for granted is held in place by forces that, while currently stable, are not guaranteed forever. That what we have is precious not just because we need it, but because it's rare. Because most places in the universe don't have it. Venus has an atmosphere, too much atmosphere, actually. 90 times denser than Earth's, made almost entirely of carbon dioxide, hot enough to melt lead. But Earth is just right, massive enough to hold an atmosphere, small enough that it's not crushingly dense, far enough from the sun to be comfortable, close enough to be warm, protected by a magnetic field, stocked with the right gases in the right proportions. We live at the bottom of a very thin, very precious ocean of air, an ocean that's been here for over 4 billion years, an ocean that makes every breath possible, every sunset beautiful, every sound audible. An ocean we're about to imagine disappearing. But first, take another breath. Notice it. Feel the air fill your lungs. Appreciate what you're about to explore losing. So, we've established what the atmosphere is and what it does. Now comes the question that probably sounds a bit absurd when you first hear it. How exactly would a planet lose its atmosphere? Because it's not like air just leaves. It's not as if the atmosphere might decide one day that it's had enough of Earth and wants to try living on Mars instead. Atmospheres don't have agency. They don't make decisions. They're just collections of molecules held in place by gravity, and they tend to stay where they are unless something actively removes them. So, what could remove them? Let's talk about the real ways planets lose their atmospheres, because this has happened before, It's happening now, actually, on various worlds throughout the solar system. It's not science fiction. It's planetary science. The most common way to lose an atmosphere is through a process called solar wind stripping. And to understand this, we need to talk about what solar wind actually is. The Sun, despite being a sphere of hot gas, is not a calm place. Its surface, well, it doesn't have a solid surface, but the visible layer we think of as its surface is roiling with activity. Magnetic fields twist and break. Plasma erupts in enormous loops. And constantly, continuously, the Sun is shedding particles into space. Protons, electrons, the occasional heavier nucleus, all streaming outward in all directions at speeds of hundreds of miles per second. This is the solar wind. It's not wind in the atmospheric sense. There's no air in space to push around. It's a wind of charged particles, and it's blowing past Earth right now, has been for billions of years, will continue until the Sun dies. Most of the time, we don't notice it. Earth has a magnetic field, generated by that churning, molten iron core we talked about earlier, and this magnetic field deflects the solar wind around us. The charged particles can't easily cross magnetic field lines, so they flow around Earth like water flowing around a rock in a stream. We're protected. But a magnetic field isn't a perfect shield. Some particles get through, particularly near the poles where the field lines converge. When these particles hit the upper atmosphere, they excite atoms and molecules, causing them to glow. This is the aurora, the northern and southern lights. It's beautiful. It's also a reminder that the solar wind is constantly trying to erode our atmosphere, and our magnetic field is constantly deflecting it. Now, what happens to a planet without a magnetic field? Mars. That's what happens. Mars had a magnetic field once. We know this because ancient rocks on Mars show remnant magnetism. They were magnetized when Mars had an active dynamo, and they've held onto that magnetization. But somewhere around 4 billion years ago, Mars's core cooled enough that the dynamo shut down. The magnetic field disappeared. Without that protection, the solar wind hit the upper atmosphere directly. Charged particles transferred their energy to atmospheric molecules, giving those molecules enough velocity to escape Mars's gravity. Not all at once. This is a gradual process. But year after year, century after century, million years after million years, Mars bled air into space. It took a long time. We're talking hundreds of millions of years. But eventually, Mars lost most of its atmosphere. What's left is about 1% the density of Earth's atmosphere. It's still there, technically. Mars has air. You just can't breathe it, and there's so little of it that liquid water can't exist on the surface anymore. This is solar wind stripping, and it's how most rocky planets without magnetic fields lose their atmospheres over geological timescales. Could it happen to Earth? Yes, eventually. If our magnetic field failed, and it will billions of years from now when the core cools, Earth would start losing atmosphere to solar wind stripping. But we're talking about a process that takes hundreds of millions of years. It's not sudden. It's not something you'd notice in a human lifetime, or even in the lifetime of human civilization. We have time. Lots of time. Another way to lose atmosphere. Impact events. Specifically, really big impact events. Imagine an asteroid or comet, something truly massive, hitting Earth at cosmic speeds. We're talking tens of miles per second. The energy released when that much mass moving that fast suddenly stops. It's equivalent to billions of nuclear weapons going off simultaneously. The impact would vaporize rock. It would create a crater hundreds of miles across. It would send ejecta, shattered, molten rock, flying into space. and some of that ejecta would be moving fast enough to escape Earth's gravity entirely, taking atmospheric gases with it. Could an impact blow away all of Earth's atmosphere? Probably not. Earth is fairly massive, and 5 quadrillion tons of air is a lot to remove all at once. But a large enough impact could blow away a significant fraction of it, maybe 10 or 20%, which would be, not ideal. The good news is that impacts large enough to do this are rare. The solar system has mostly cleaned itself out of giant debris over the past few billion years. The age of massive atmosphere-stripping impacts is largely over. Mostly. We still keep an eye on large asteroids just in case, but the odds of something truly catastrophic hitting Earth in any given year are very, very small. There's also thermal escape. This is where lighter molecules in the upper atmosphere simply leave. They're moving fast. Temperature is just molecular motion after all, and if they're moving fast enough and they're high enough in the atmosphere where collisions are rare, they can reach escape velocity and drift off into space. This happens to Earth. We're losing hydrogen and helium all the time through thermal escape. But hydrogen and helium are the lightest elements. They're easy to lose. Heavier molecules, nitrogen, oxygen, carbon dioxide, don't reach escape velocity at Earth's temperature. They stay put. So thermal escape isn't going to remove our atmosphere anytime soon. We'd lose all our hydrogen first, which would take billions of years, and even then the nitrogen and oxygen would remain. So those are the real ways planets lose atmospheres. Solar wind stripping over hundreds of millions of years. Giant impacts that are rare and probably wouldn't remove all the air anyway, and thermal escape of light elements that doesn't affect the bulk of our atmosphere. None of these are sudden. None of these would happen overnight. Atmospheres are remarkably stable once they're established, especially on planets with magnetic fields and relatively few giant impacts. But for our thought experiment tonight, we're not interested in gradual loss over geological time. We're imagining something impossible. We're imagining the atmosphere disappearing rapidly, not over millions of years, but over hours, maybe days. This can't happen through any natural process we know of. There's no mechanism that could remove 5 quadrillion tons of air quickly. But that's why it's a thought experiment. We're imagining the impossible to understand what's normally invisible. So let's set up our scenario. Imagine that somehow, through some cosmic mechanism we won't try to justify, because we can't, Earth's atmosphere begins to disappear. Not gradually over eons, but rapidly enough that people would notice. Rapidly enough that it would matter. We could imagine 2 versions of this. Instant loss, where the atmosphere vanishes all at once in a moment, or gradual loss, where it disappears over the course of, say, a day or 2. Both versions teach us something different about what the atmosphere does and why we need it. Both are impossible, but in different ways. Both are worth exploring. Let's think about what would happen first in either scenario, because whether the air disappears instantly or over the course of hours, there are immediate effects that would be impossible to ignore. The first thing you'd notice, and by notice I mean be violently aware of, is the pressure change. Remember, atmospheric pressure at sea level is 14.7 pounds per square inch. That's the weight of all that air above you, pulled down by gravity. Your body is built for this pressure. Your lungs expect it. Your blood is under pressure that balances against it. Your cells are full of dissolved gases at concentrations determined by external pressure. If the pressure drops suddenly, those gases try to equilibrate. Dissolved gases in your blood, mostly nitrogen, start to come out of solution. This is what happens to divers who ascend too quickly. Decompression sickness. Nitrogen bubbles form in the bloodstream, causing pain, tissue damage, potentially fatal blockages. But decompression sickness from too rapid diving is from going from high pressure to normal pressure. We're talking about going from normal pressure to no pressure, to vacuum. Your body wouldn't explode. Despite what some science fiction movies suggest, humans don't explode in vacuum. Your skin is strong enough to hold you together, but you would swell slightly as gases inside you expanded. The most dangerous place for this is your lungs. If you held your breath as the pressure dropped, the air in your lungs would expand and would rupture your lung tissue. This is why the advice for sudden depressurization is exhale. Don't hold your breath. Let the air out. It's going to come out anyway. Better to let it out through your mouth than through ruptured alveoli into your chest cavity. The air would rush out of your lungs, all of it. You'd feel your chest deflate. You'd try to inhale instinctively, desperately, but there'd be nothing to breathe. Nothing at all. Consciousness is surprisingly dependent on oxygen reaching the brain. If you stop breathing, you have about 15 seconds before you pass out. That's assuming your blood still has some oxygen in it that's being circulated. In a sudden decompression, you might have slightly less time as the oxygen in your blood off-gasses. 15 seconds, maybe 10. That's how long you'd be conscious. Long enough to realize something was terribly wrong. Long enough to panic. Not long enough to do anything about it. After you lose consciousness, brain damage starts in 1 to 2 minutes. Death follows shortly after, maybe 2 to 3 minutes total. It's fairly quick as deaths go. Not instant, but not prolonged. The moisture in your mouth and on your eyes would boil. Not because it's hot, because there's no pressure. Water boils at room temperature in vacuum. You'd feel your tongue and eyes and any exposed mucous membranes start to bubble and freeze simultaneously, because evaporation is a cooling process. It would be deeply unpleasant for those few seconds you're conscious. This is what happens to a human body. Now multiply this by 8 billion. Every person on Earth would be experiencing this simultaneously. No exceptions. Everyone needs air. It doesn't matter if you're young or old, fit or frail, prepared or unprepared. Without air, you have seconds. The only people who might survive the initial pressure loss are those who happen to be in sealed environments with their own air supplies. The International Space Station, they're already in a vacuum-protected environment, so nothing would change for them immediately. They'd be fine for as long as their life support held out. Submarines, if they're sealed and submerged, would maintain pressure temporarily. The crew would have whatever air is in the submarine. Hours, maybe. Days, if they're very lucky and very careful with their oxygen. But eventually they'd have to surface, and when they did, there'd be no air to breathe. Deep underground bunkers with life support systems might sustain people for weeks or months. But without plants to replenish oxygen, without an atmosphere to draw from, even stored oxygen runs out eventually. But let's think beyond just the human impact, because the atmosphere does a lot more than give us air to breathe, and when it's gone, all of those other functions fail too. Water would start to boil immediately, not from heat, from lack of pressure. Oceans, lakes, rivers, the moisture in soil, the sap in trees, all of it would start to vaporize. On Earth's day side, where the sun is shining, this would happen rapidly. Water would turn to steam, and that steam would escape to space because there's no atmosphere to hold it. On the night side, water would freeze instead. Without atmospheric pressure, without the greenhouse effect keeping temperatures moderate, the temperature would plummet. Water would turn to ice. That ice would slowly sublimate, turn directly from solid to vapor, and that vapor would also escape to space. Earth's water, that beautiful blue covering most of the planet's surface, would begin to disappear. Not all at once. The oceans contain a lot of water and thermal mass matters, but visibly, measurably over hours and days. The temperature would become extreme. On the day side, in direct sunlight, the temperature would spike. Without atmosphere to distribute heat, without the moderating effect of air circulation, surfaces in direct sunlight would heat up rapidly. We're talking hundreds of degrees Fahrenheit, hot enough to boil water, though there'd be no liquid water left to boil. On the night side, temperatures would plummet. Without atmosphere to trap heat, without the greenhouse effect, the temperature would drop to hundreds of degrees below zero, cold enough to freeze carbon dioxide, cold enough that any remaining water would be solid ice. The terminator, the line between day and night, would be the only place with relatively moderate temperatures, and moderate is relative. You'd still be in vacuum, so you'd still die, but at least you wouldn't be cooked or frozen first. Meteorites would start hitting the surface. All of them. Every piece of space debris that normally burns up in the atmosphere would now reach the ground. Most of these are small, dust particles, pebbles. They wouldn't do much damage individually, but collectively, constantly, it would be like a very slow sandblasting of the entire surface. And then there's the radiation. Ultraviolet radiation from the sun, normally blocked by the ozone layer, would flood the surface. Cosmic rays, normally deflected or absorbed by the atmosphere, would hit unimpeded. X-rays from solar flares would reach the ground. Any life on the surface would be subjected to a radiation dose that would be lethal within hours. DNA would be damaged. Cells would die. Even if you somehow had air to breathe, even if you somehow maintained pressure, the radiation alone would be deadly. The surface of Earth would become, very quickly, utterly inhospitable to life. A dead zone. Silent, because there's no air to carry sound. Dark on the night side, blazing bright on the day side. Airless. Waterless. Hostile. And this is just the beginning. This is just what happens in the first hours. But for now, just know this. Losing the atmosphere isn't just losing something to breathe. It's losing the entire system that makes Earth habitable. The pressure that keeps water liquid and blood flowing properly. The temperature regulation that keeps us from freezing or cooking. The protection from radiation and space debris. The water cycle. The sound. Everything. Take another breath. Hold it for a moment. Feel what it's like to have air in your lungs, then let it out. Because next, there won't be any air to breathe. There won't be anything to hold. And understanding what that would be like helps us appreciate what we have right now. The invisible ocean that keeps us alive. We've talked about how atmospheres can be lost and what the general effects would be. Now let's slow down time. Let's walk through what would actually happen in those first seconds if the atmosphere disappeared. Not to be morbid, but to understand. To make visible what's usually invisible by imagining its absence. Let's set up our scenario carefully. It's an ordinary Tuesday afternoon. The date doesn't matter. Pick your favourite day. The weather is pleasant. Maybe there are clouds in the sky, maybe it's clear. People are going about their lives. Someone is walking their dog. Someone else is sitting in a cafe, drinking coffee, watching the world go by. A child is playing in a park. A farmer is checking crops. An office worker is staring at a computer screen, thinking about lunch. Life is happening as it does in all its ordinary, unremarkable beauty. And then, somehow, impossibly, the atmosphere begins to disappear. We'll imagine this happens quickly but not instantaneously. Not a sudden pop into vacuum, but a rapid thinning over the course of maybe 30 seconds to a minute. This gives us time to notice what's happening, time to experience the sequence of events. It's not realistic. Nothing about this scenario is realistic, but it helps us understand the atmosphere's role by watching what happens when it's removed piece by piece. The first thing you'd notice is the sound. Actually, let me rephrase that. the first thing you'd notice is the absence of sound. Sound travels through air. It's a pressure wave, a vibration that propagates through the medium of gas molecules bouncing into each other. No air, no sound. As the atmosphere thins, sound would become quieter, more muffled, like you're underwater or wearing earplugs. Conversations would become harder to hear. The ambient noise of the world, traffic, birds, wind in the trees, the rustle of leaves, the distant hum of an airplane, someone's music playing from a window, all of it would fade. Within 10 or 15 seconds, as the air continued to thin, you'd notice that voices sounded strange, thin, distant. You'd have to concentrate to hear someone speaking right next to you. If someone shouted from across the street, you wouldn't hear them at all. The world would be getting quieter, and you'd probably think something was wrong with your ears. By 30 seconds, the air would be thin enough that sound barely travels. You could shout at someone standing next to you, and they might hear a faint whisper, or they might hear nothing at all. Your own voice would sound wrong in your head. You'd feel the vibrations in your skull, but hear nothing external. This is deeply unnerving, by the way. Humans are not built for silence. We navigate the world partially by sound. We orient ourselves by ambient noise. When sound stops working properly, when you can't hear your own footsteps or your own voice or the world around you, your brain starts to panic. Something is fundamentally wrong, and every instinct you have knows it. But you wouldn't have much time to worry about the silence because the pressure would be dropping too. Your ears would pop, painfully. That pressure equalization that happens when you're in an airplane or driving up a mountain. Imagine that, but much more intense and much faster. The pressure differential between your inner ear and the outside world would spike, and your eardrums would flex inward trying to equalize. Pop, pop, pop. Except you probably wouldn't hear the pops because sound isn't traveling properly anymore. You just feel them, sharp little pains in your ears, uncomfortable and wrong. And as the pressure continued to drop, you'd start to feel it in your chest. Breathing would become difficult, not because there's no air yet, there's still some air, just less of it, but because your lungs are used to a certain pressure. They're designed to work against 14.7 pounds per square inch of external pressure. As that pressure drops, breathing feels wrong, like you're at high altitude, except you're not moving, you're just standing there and the air is leaving. You'd start breathing faster, trying to compensate. Your heart rate would increase. You might feel dizzy, lightheaded. Your body would know something was very, very wrong. Even if your conscious mind hadn't caught up yet, adrenaline would flood your system. Fight or flight response, except there's nothing to fight and nowhere to flee. At this point, people around you would be noticing too. Everyone would be experiencing the same thing. The silence, the ear popping, the difficulty breathing. There might be confusion, questions without answers, panic starting to set in. Someone might look up at the sky and notice that it looks wrong, different, because the sky would be changing. The blue sky, that beautiful scattered light from air molecules, would be fading. As the atmosphere thins, there's less air to scatter the sunlight. The sky would take on a darker quality, not black yet, but a deep, purplish blue, darker than you've ever seen it, like twilight. Except the sun is still high in the sky. And you'd be able to see stars during the daytime. Faint at first, the brightest ones, but becoming clearer as the air continues to thin. Venus would be visible, Jupiter maybe, the brightest stars. It would be beautiful, in a terrifying sort of way. The sun itself would look different too. Normally, the atmosphere scatters some of the sun's light, making it look yellowish. As the atmosphere disappears, the sun would appear whiter, brighter, harsher, more like how it looks from space. You wouldn't want to look at it directly. You still shouldn't, actually, even with less atmosphere. But in your peripheral vision, you'd notice the change. Shadows would become sharper, without air to scatter light, without that diffuse illumination we're used to. Shadows would have hard edges. The contrast between light and dark would be stark. Everything would look high definition, hyper-real, like the contrast has been turned up too high. The temperature would start to change too. Not dramatically yet. Thermal mass takes time to heat or cool. But you'd notice the air feeling different on your skin. If you were in direct sunlight, you might feel warmer. In shade, you might feel a slight chill. The air isn't there to buffer temperature changes anymore. By about 45 seconds to a minute, the air would be thin enough that you couldn't breathe effectively anymore. You could try, your lungs would still move, you'd still be inhaling and exhaling, but there wouldn't be enough oxygen to sustain consciousness. Your vision would start to narrow, tunnel vision setting in as your brain becomes oxygen-starved. Colours might seem brighter or stranger. Your thoughts would become fuzzy, disconnected. This is when you'd lose consciousness, not from anything dramatic, just from lack of oxygen. Your brain needs a constant supply, and when it doesn't get it, it shuts down. It's a safety mechanism, actually. When things go catastrophically wrong, when the system can't be maintained, the brain goes offline to preserve itself for as long as possible. You'd have about 15 seconds of consciousness once the air became too thin to breathe effectively. 15 seconds to think whatever final thoughts occur to you. To notice that the world has become silent, that the sky is the wrong colour, that breathing doesn't work anymore, to feel confusion or fear, or perhaps a strange sort of calm as consciousness fades. And then darkness. Not death yet. Your heart would still be beating. Your cells still have some oxygen in reserve. But consciousness would be gone. After you lose consciousness, you'd have perhaps another minute or two before brain damage becomes irreversible. During this time, if the atmosphere somehow returned, if air pressure was restored and you were given oxygen, you might survive. You'd have some stories to tell. The window is small, but it exists. But in our scenario, the atmosphere isn't returning. It's continuing to disappear. As the pressure drops to near vacuum, things start to happen to your body that would be uncomfortable if you were conscious to experience them, which, mercifully, you're not. The moisture on your tongue, in your mouth, on the surface of your eyes, it would start to boil. Water boils at lower temperatures when pressure decreases. This is why water boils faster at high altitudes. There's less atmospheric pressure. At the pressure of space, which is effectively zero, water boils at any temperature above its freezing point, including body temperature. So your saliva would bubble. The tear film on your eyes would evaporate. It's not boiling from heat. The temperature hasn't changed much yet. It's boiling from lack of pressure. The water molecules are energetic enough to escape into gas form, and without atmospheric pressure to keep them liquid, they do. This evaporation is actually a cooling process, which is why your tongue and eyes would also start to freeze. Evaporation absorbs heat, so you'd have the strange situation of moisture boiling and freezing simultaneously. Physics can be paradoxical like that. Your body would swell slightly. Not dramatically. You're not going to inflate like a balloon in a cartoon. But gases dissolved in your tissues and blood would start to come out of solution, expanding as they do. You'd puff up a bit. Your abdomen would distend as gases in your intestines expanded. Your face might look slightly swollen. It's called ebulism, if you want the technical term. If your mouth happened to be closed, if you held your breath as the pressure dropped, which would be instinctive, even though it's exactly the wrong thing to do, your lungs could rupture from the expanding air inside them. This is why the advice in any rapid decompression scenario is always exhale. Let the air out. Don't hold your breath. Your lungs are delicate and they can't handle much pressure differential between inside and outside. But assuming you did exhale, or that the air was pulled from your lungs by the pressure differential, your chest would deflate completely. The lungs would collapse, not damaged necessarily, just empty, like balloons with no air in them. Your heart would still be beating, though, for a surprisingly long time, actually. The heart is a muscle, and it can continue to contract even without oxygen for a couple of minutes. It would be pumping blood that has progressively less oxygen in it, pumping it to tissues that are starting to die from hypoxia. But it would keep trying. The heart is remarkably persistent. Eventually, though, the heart would stop, maybe 2 or 3 minutes after you lost consciousness. The muscle simply can't maintain contractions without oxygen. At that point, death would be effectively inevitable. Even if the atmosphere returned, even if you were given oxygen and medical attention, the damage to your brain and other organs would be too severe. But you wouldn't know any of this because you'd be unconscious, which is, in a strange way, a mercy. The human body is fragile, but it's also resilient in unexpected ways. The most fragile part of us, the part that can't tolerate these conditions even briefly, is consciousness itself. That goes first. Everything else takes a little longer. Now let's think about what's happening around you during these first seconds and minutes. 8 billion people are experiencing this simultaneously. Everyone, everywhere. The astronauts on the International Space Station are fine. They're in a sealed environment. They already live in what's effectively a submarine in space. They'd notice their communications failing, Earth going silent, but their immediate environment wouldn't change. But everyone else? Everyone on the surface? They're going through exactly what we just described. People in airplanes are in particularly unfortunate situations. Commercial aircraft maintain cabin pressure using compressed air from outside, bled off from the engines. As the atmosphere disappears, there's no more outside air to compress. The cabin would depressurize rapidly. Oxygen masks would drop, standard procedure. But there's no oxygen to flow through them. The masks work by providing concentrated oxygen from the outside air. No outside air, no oxygen. The pilots might have emergency oxygen tanks, but those would last minutes, not hours, and there's nowhere to land anyway. People in submarines that are submerged would actually be okay temporarily. Submarines are designed to maintain internal pressure independent of external pressure. In fact, they're designed to withstand much higher external pressures than they'd experience from losing the atmosphere. So a submarine crew underwater would have hours of air, possibly days. But they'd know something was catastrophically wrong when they lost radio contact with the entire world. Every transmission would go silent. They'd be alone in the deep, with no idea what happened on the surface. Vehicles would coast to stops. Not because engines need air to run. Well, actually, internal combustion engines do need air for combustion, so cars and trucks would sputter and stall as the air thinned. The engine needs oxygen to burn fuel. No air, no combustion, no power. Electric vehicles would keep running for a bit longer, at least until their drivers lost consciousness and took their feet off the accelerators. Then they'd coast until friction slowed them to a stop. The world would go quiet. Not just from lack of sound transmission, but because all the noise-making things, traffic, aircraft, industrial machinery, anything that requires air to operate, would stop. The constant background hum of civilization, the noise we don't even notice until it's gone, would fade to nothing. Plants would be stressed immediately. Photosynthesis requires carbon dioxide from the air. No air, no CO2, no photosynthesis. The stomata on leaves, the tiny pores that let gas exchange happen, would close reflexively, trying to conserve water. But it wouldn't matter. Without atmospheric pressure, the water in plant tissues would start to vaporize anyway. The leaves, the stems, the delicate machinery of plant life, it would all start to desiccate, to dry out, to fail. Animals would fare the same as humans. Mammals, birds, reptiles, amphibians all need air to breathe. Insects too, though they breathe through spiracles rather than lungs. It doesn't matter how you breathe when there's nothing to breathe. Everything that requires atmospheric oxygen would die within minutes. No exceptions, no survivors. The surface would become silent, not just from lack of sound, but from the absence of life. Aquatic life would last slightly longer. Fish get their oxygen from water, not air, and water doesn't disappear instantly just because the atmosphere does. But without atmospheric pressure, the water at the surface would start to boil, especially where it's warmer, and as it boiled, it would release dissolved gases. The oxygen content of water would plummet. Fish would suffocate in water that no longer contains enough oxygen to support them. Deep sea life, far below the surface, where pressures are higher and water doesn't boil as readily, might survive longest. The deep ocean is a very different environment, largely isolated from the surface. The pressure down there comes from the weight of water above, not from the atmosphere. But even there, eventually, the effects would reach. The ocean is connected. What happens at the surface eventually affects the deep. The one place that might be genuinely okay, at least briefly, is deep underground. Cave systems, deep mines, any large enclosed space far below the surface would maintain air pressure for a while. Air doesn't teleport away instantly. It has to flow, and if there's no path to the surface, if the space is sealed by rock and distance, the air might stay trapped. But a while is relative. Maybe hours, maybe days for a really deep, well-sealed space. Eventually, though, the air would find cracks, fissures, pathways to the surface, or the temperature would change as the surface temperature spiked and plummeted, creating pressure differentials. Or seals would fail. There's no permanent refuge underground unless it's specifically engineered as a sealed habitat with life support. And even if you were in such a place, a deep bunker with stored oxygen and food and water, what then? You'd survive the initial loss of atmosphere, sure. You'd be one of maybe a few thousand people still alive, but you'd be living in what amounts to a submarine on land. No ability to go outside. No way to replenish your air supply except through whatever recycling systems you have. No plants to generate oxygen unless you brought them inside with artificial light and perfect growing conditions. You could survive weeks, maybe months if you were very well prepared. But eventually something would fail. A seal would leak. A machine would break down. You'd run out of some critical resource. And when you did, you'd be right back to the same problem. No atmosphere means no survival on the surface. This is what the first seconds and minutes would look like. This is what happens when you remove that invisible ocean we swim in. This is why the atmosphere, that thin skin we never think about, is so utterly essential. But here's what's important to remember as we walk through this. This is a thought experiment. This won't happen. This can't happen. There's no natural mechanism that would remove Earth's atmosphere this quickly. We're exploring this not to frighten, but to understand, to appreciate. When you imagine losing something, when you walk through what that loss would entail, you come to value what you have. And what we have right now is something extraordinary. An atmosphere that's been stable for billions of years. An invisible ocean that gives us breath, protects us from radiation, keeps our water liquid, carries sound to our ears, paints the sky blue. An atmosphere that makes life possible in every moment of every day. Take a breath. You can. The air is still there. Feel it fill your lungs. Notice how easy it is, how natural, How completely unremarkable. And now let's continue our journey, because these first seconds are just the beginning. Now let's move forward in time. Let's look at what happens in the hours after the atmosphere disappears. The immediate crisis is over. Everyone who was going to lose consciousness has lost consciousness. But the planet itself is just beginning to change. And the changes are going to be significant. Let's start with what you'd see if you could somehow observe Earth from space during these hours. Maybe you're on the International Space Station, which is still fine. Sealed environment, its own life support. You're watching your home planet through the window, and you're seeing it transform in ways that are both beautiful and heartbreaking. The first thing you'd notice is the sky. From space, Earth's atmosphere normally shows up as a thin blue haze around the planet. It's that layer of scattered light, that visible reminder that Earth has air. As the atmosphere disappears, that haze would fade. Within minutes, it would be gone. Earth would look more like the moon, just rock and water, no atmospheric envelope. Sharp, harsh, no soft edges. The clouds would be evaporating, not floating away. There's nowhere for them to float to, but dissipating. Water vapor in the atmosphere would be expanding, escaping. The beautiful swirls of weather systems, the hurricanes and typhoons and cloud formations that make Earth recognizable from space would be disappearing. Within an hour, the cloud cover would be mostly gone. You'd be able to see the surface more clearly than you ever could before. No atmosphere to blur the view. No clouds to block it. You'd see continents and oceans in sharp detail. Every mountain range visible, every desert, every coastline. It would look clearer, crisper, also emptier somehow, more desolate. And you'd start to notice something strange happening to the oceans. Water without atmospheric pressure behaves differently. On the day side of Earth, where the sun is shining, the surface of the ocean would start to boil. Not from heat, the sun hasn't gotten any hotter. But without pressure, water boils at lower temperatures. At zero pressure, water boils at any temperature above freezing. So the surface layer of the ocean would be turning to steam. You'd see it from space as a sort of haze rising from the oceans, like fog, but more active, more urgent. The water is literally boiling, vaporizing, escaping into space as steam. This vapor has nothing to hold it down. No atmospheric pressure, so it just keeps going up and up until it's lost to space. The oceans wouldn't disappear immediately. There's a lot of water down there, about 1.4 billion cubic kilometers of it. That's a truly staggering amount, and water has high thermal mass. It takes a lot of energy to heat it or boil it, so the deep ocean would stay liquid for a while. Hours, maybe days. But the surface, the top layer, that would be boiling off steadily. If you were observing from the ISS, you'd see the ocean shrinking, slowly, measurably. The water level dropping as vapor escapes to space. The coastlines would be advancing inland as the ocean level dropped, beaches getting wider, harbors going dry, continental shelves exposed. On the night side of Earth, something different would be happening. Without atmosphere, without the greenhouse effect to trap heat, the temperature would be plummeting. We're talking hundreds of degrees below zero. Water exposed to those temperatures would freeze. Solid. Ice forming rapidly on the surface of the nightside ocean. So you'd have this strange situation where Earth has boiling oceans on one side and freezing oceans on the other. The terminator line, the boundary between day and night, would be the only place where water might remain liquid, at least temporarily. But even there, without pressure, liquid water is unstable. It wants to either boil or freeze. There's no comfortable middle ground anymore. Now let's think about what's happening on the surface itself. The temperature is becoming extreme. On the day side, without atmosphere to diffuse the sunlight, without air to distribute heat, the surface is heating up rapidly. Direct sunlight on airless worlds is intense. The Moon, for comparison, reaches temperatures around 250 degrees Fahrenheit in direct sunlight. Earth would be similar, maybe slightly cooler because Earth has more thermal mass, more materials that can absorb heat. But we're still talking well above the boiling point of water. Any water on the surface, lakes, rivers, puddles, the morning dew, the moisture in soil would be boiling away. Steam rising, vapor escaping. The landscape would be transforming from wet to dry in a matter of hours. Plants that had already died from lack of air would now be desiccating, drying out completely. All the water in their tissues, and plants are mostly water just like us, would be evaporating. The landscape would be transforming from green and living to brown and dead, colours fading like an old photograph left in the sun. Forests would look strange. The trees would still be standing. There's no wind to knock them over, no air for wind to exist in, but they'd be dead, dried out, brittle. The leaves would be crisp, fragile, ready to crumble at a touch if anyone were there to touch them. It would look like autumn, except everything happened at once instead of gradually over weeks. Instant autumn, permanent autumn. Grasslands would turn brown. Agricultural fields that were green with crops would become desiccated. Gardens that were carefully tended just hours ago would be dead and dry. Every living plant on the surface would be in the same state, dead, dry, preserved by the very lack of water and air that killed it. On the night side, everything would be freezing. Temperatures dropping to 200, 250, maybe 300 degrees below 0 Fahrenheit. Any remaining liquid water would freeze solid within minutes. The ground itself would contract as it cooled. Thermal expansion works in reverse. Rocks would crack from the temperature stress. You'd hear it if there were air to carry sound. The sharp crack of stone splitting, but there's no air, so it all happens in silence. And here's where things get particularly interesting from a geological perspective. The planet is rotating. Earth still spins on its axis, one rotation every 24 hours, same as always. So the day side and night side are constantly changing. A place that was in sunlight heating up to 250 degrees would rotate into darkness and start freezing, cooling to 250 below 0. Then 12 hours later, it would rotate back into sunlight and start heating up again. This temperature cycling would be brutal on materials. Imagine going from 250 degrees Fahrenheit to 250 degrees below 0 to 250 degrees again, over and over, every single day. Materials expand when heated and contract when cooled. This is usually a small effect. The coefficients of thermal expansion are typically measured in millionths per degree. But over temperature ranges of 500 degrees, that's substantial. Rocks would crack. The expansion and contraction would create stresses at grain boundaries, at weak points. Fractures would form. Over days and weeks, solid rock would start to break apart, just from temperature cycling. Any human structures, buildings, roads, bridges, would be subjected to stresses they were never designed to handle. We build things for Earth's climate. Temperature ranges from, negative 40 to 120 degrees Fahrenheit in extreme environments, not 500-degree swings every day. Concrete would crack and crumble. The temperature cycling would break down the structure. The rebar inside would expand and contract at different rates than the concrete. Foundations would shift. Walls would develop fractures. Steel would become brittle in the extreme cold, then expand and deform in the heat. The crystal structure of metal changes with temperature. Cold makes it brittle. Heat makes it soft. Cycling between extremes would fatigue it, create stress fractures. Glass would shatter. It's already fairly brittle, and it doesn't handle thermal stress well. Windows would crack, solar panels would break. Anything made of glass would be destroyed within days of temperature cycling. Plastics would become brittle and break. The polymer chains would be damaged by UV radiation. Remember, full-strength UV is hitting the surface now. And then stressed by temperature changes. Plastic bottles, car interiors, synthetic fabrics, all of it degrading rapidly. Everything we've built would be falling apart. Not from violence, not from explosions or earthquakes or storms, just from physics, from the inexorable process of thermal stress in an environment that no longer has the moderating influence of atmosphere. Cities would still be standing. Buildings don't collapse just because it gets hot or cold, but they'd be degrading, damage accumulating, cracks forming, materials failing. Give it weeks or months and the damage would be severe. Give it years and most structures would be unrecognisable. Let's talk about what else is happening in these first hours. Meteorites are hitting the surface. Remember, the atmosphere normally burns up tons of space debris every day. Small rocks, dust particles, the occasional larger chunk. All of it hits the atmosphere at cosmic speeds, sometimes tens of miles per second, and vaporizes from friction. We see them as shooting stars. They're beautiful. They're also the atmosphere doing its job, protecting us from a constant rain of space debris. Without atmosphere, all of that is hitting the ground. Most of it is small, dust-sized particles. They'd hit like tiny bullets, moving at kilometers per second. They wouldn't do much damage individually, a microscopic crater maybe. But collectively, constantly, every exposed surface would be getting pitted, eroded, damaged at a microscopic level. It's like a very gentle sandblasting of the entire planet. Occasionally something larger would hit. A pebble, a fist-sized rock, something the size of a baseball. These would impact with enough energy to create actual craters. Small craters, but craters nonetheless. The kinetic energy of something moving at tens of miles per second is enormous. Even a small object carries tremendous energy. Over time, days, weeks, months, the surface would accumulate impact scars. Thousands of them, millions of them. Earth would start to look more like the moon, covered in small craters from all the debris that normally burns up harmlessly. The surface would be getting sandblasted and cratered simultaneously. And there's radiation. So much radiation. The sun emits ultraviolet radiation, UV light, constantly. It's part of the sun's normal spectrum. On Earth, the ozone layer absorbs most of it. That's what the ozone layer is for. It's our UV shield. Without it, without any atmosphere at all, UV radiation floods the surface at full strength. UV light damages DNA. It breaks the chemical bonds of the DNA molecule. This is why too much sun exposure causes skin cancer. Your DNA gets damaged, errors accumulate. Sometimes cells become cancerous and start dividing out of control. But that's from regular Earth sunlight with most UV already blocked. Full-strength UV, the kind that's now hitting the airless surface, would be sterilizing. Any life that somehow survived the lack of air, maybe some bacterial spores in a protected crevice, some extremophile microbes in a sealed pocket, would be killed by UV radiation within hours. The radiation would penetrate anything exposed to the sky. Surfaces would be sterilized. Nothing living. Nothing that could become living. There's also cosmic radiation, high-energy particles from space, mostly protons, some alpha particles, some heavier nuclei, constantly bombard Earth. They come from the sun during solar flares, but also from distant supernovae, from pulsars, from various violent events across the galaxy. The atmosphere normally absorbs or deflects most of them, Earth's magnetic field helps too, channeling them toward the poles. But without atmosphere, they hit the surface directly. Cosmic rays don't just damage DNA, they can break apart atoms, create isotopes, cause nuclear reactions in matter. It's not immediately destructive like UV, but over time it would make the surface radioactive. Materials would accumulate unusual isotopes they normally wouldn't have. Rocks would develop radioactivity. The surface would become a place you wouldn't want to visit, even if you could breathe. Let's think about what happened to water specifically, because it's worth understanding in detail. Earth has a lot of water, oceans covering 71% of the surface, ice caps at the poles, lakes and rivers, groundwater, the moisture in soil and organisms, all told about 1.4 billion cubic kilometres. When the atmosphere disappeared, all of this water became unstable. On the surface, in direct sunlight, water would boil. The vapour would rise. No atmosphere to stop it, no pressure to condense it back to liquid, and eventually escape to space. Earth's gravity isn't strong enough to hold on to water vapour at these temperatures without atmospheric pressure to help. In shadow, in darkness, water would freeze. Ice doesn't boil, but it does sublimate, turn directly from solid to vapour, especially in vacuum. Slowly, much more slowly than liquid water boils. But still, ice in vacuum gradually turns to vapour and escapes. You can see this on comets. They have tails because ice is sublimating off their surface as they get close to the sun. Deep water, underground water, deep ocean water would be more protected. Temperature takes time to propagate through matter. Rock is an insulator. Water buried under meters or kilometers of rock would stay liquid for days, maybe weeks. The deep ocean, kilometers below the surface, would take even longer to freeze or boil. But eventually, everything makes its way to the surface. Pressure gradients drive flow. Temperature gradients drive convection. Water would gradually work its way up, and as it reached the surface, it would be lost. Over the course of weeks to months, Earth would be losing its water. The oceans would evaporate, dayside boiling, nightside freezing and sublimating. Lakes and rivers would disappear within days. Groundwater near the surface would sublimate. The water cycle, that beautiful system that's been operating for billions of years, that moves water from ocean to atmosphere to precipitation to rivers back to ocean, would be breaking down. And there's something poetic in a sad way about this. Water made Earth habitable. Water erosion created our landscapes, the Grand Canyon, river valleys, coastlines. Water hosts life. Water is the medium in which chemistry happens, in which life evolved, in which every biological process operates. We're water creatures living on a water planet, and without atmosphere, water can't exist on the surface. It leaves. It's expelled to space, lost, gone. Within weeks, Earth would be dry, not completely. There'd still be ice in deep caverns, water trapped in rocks deep underground, maybe some deep subterranean reservoirs protected by kilometers of insulating rock. But the surface would be a desert. The oceans would be gone, leaving behind empty basins full of salt and sediment. Earth would look more like Mars, a dry, barren world with ancient lake beds and river valleys as the only evidence that water was ever there. Now you might be wondering, what about the ISS? What about those sealed environments we talked about? They'd be fine, at least for a while. The International Space Station has life support systems, oxygen recyclers that split CO2 back into oxygen, carbon dioxide scrubbers, water recycling that processes urine and condensation back into drinking water. It's impressive technology. They're designed to operate for months without resupply. The crew would be okay temporarily. But they'd have a serious problem: resupply. The ISS depends on regular shipments from Earth. Food, equipment, spare parts, eventually even oxygen and water. Though those are recycled, the recycling isn't 100% efficient, so you need to replenish the losses periodically. Without anyone alive on Earth, without anyone launching rockets, without anyone manufacturing the supplies they need, the ISS crew would have a finite lifetime. Months, maybe 6 months if they stretched their supplies and were very careful. They'd be looking down at Earth, watching it transform, knowing they were the last humans conscious anywhere. It would be... lonely doesn't seem like a strong enough word. Devastating, maybe. They'd watch the clouds disappear, watch the oceans shrink, watch the planet die, and they'd know there was no rescue coming, no resupply, no way home. Submarines that happened to be submerged when the atmosphere disappeared would face similar problems. They'd have air for days, maybe a week if they were careful, and had a full crew to manage resources. Submarines have pretty sophisticated air recycling. They have to, since they can spend months underwater. But they're not designed to operate indefinitely without surfacing. Eventually they'd have to come up. And when they did, when they opened the hatches expecting air, there'd be nothing. Their choices would be stay submerged and suffocate when the air runs out, or surface and suffocate immediately. Neither option is appealing. Any deep bunkers with life support would last the longest. If you had a well-stocked bunker with air recycling, food, water, power from nuclear or geothermal sources, you could potentially survive for months. The record for sealed environment survival is actually pretty good. The Biosphere 2 experiment kept people alive in a sealed system for 2 years, though that had the advantage of sunlight for plants and a fairly large volume. Underground, without plants, without natural light, you'd be dependent entirely on technology and stored resources. And eventually, something would fail. A pump would break and you'd have no replacement parts. A seal would crack from temperature stress. You'd run out of some critical supply, maybe vitamins, maybe trace minerals you didn't think to stock. Or maybe you'd just go crazy from isolation. Humans aren't built to live in sealed boxes forever. We're social creatures. We need space, variety, other people, nature, sunlight. Living in a bunker indefinitely isn't really living. It's just slowly dying in a slightly more comfortable environment. So even the survivors in sealed environments, they're not really surviving long term. They're just delaying the inevitable. Without an atmosphere, without the Earth system functioning, there's no future. Just a countdown until something critical fails. Here's what's important to understand about these first hours. Earth is transforming from a living world to a dead one. Not slowly, not over geological time, but rapidly, measurably, within hours and days. The atmosphere was the difference. That thin skin of air, that invisible ocean we never think about, was all that stood between Earth and being just another airless rock in space. Without it, the surface becomes hostile almost immediately. Temperature extremes that nothing evolved to handle. No water in liquid form. Radiation at sterilizing levels. Meteor impacts. Silence. No air to carry sound. Darkness on one side, harsh light on the other with no comfortable in-between. Everything that made Earth habitable, gone. And it happens fast. Not instantly, but over hours and days rather than millennia. The planet itself is resilient in some ways. The core is still molten. The magnetic field still works. The rock is still solid. Earth as a physical object is fine. But the surface, the biosphere, the thin layer where life exists, that's fragile. That requires constant maintenance by the atmosphere. Take away the atmosphere, and it all falls apart. But remember, this is a thought experiment. This isn't going to happen. There's no mechanism that would remove Earth's atmosphere this quickly. We're safe. The air is still there, still doing its job, still protecting us. We're exploring this to understand, to appreciate. When you imagine your home planet becoming an airless wasteland, when you walk through the physics of what would happen, you start to value the invisible shield that prevents it. When you see what those first hours would look like, you understand why that thin layer of air is so incredibly important. Take a breath. Feel how easy it is, how natural, how the air is right there ready for you, how it's been there your whole life, will be there tomorrow, will be there for billions of years to come. The invisible ocean is what makes the difference between a living world and a dead one. And we have it, right now, still there, still protecting us. So we've seen what happens to Earth's surface in those first hours. It's not good. The landscape transforms, the oceans boil or freeze, the temperature becomes extreme, everything dies. But now comes a question that's worth exploring, because humans are naturally hopeful creatures. Could anything survive? Is there anywhere on Earth, any niche, any protected space where life might persist? It's a question worth asking, because life on Earth is remarkably resilient. Life has survived 5 major mass extinctions. It's survived asteroid impacts that vaporized rock and set the atmosphere on fire. It survived volcanic eruptions that darkened the sky for years. It survived ice ages that covered most of the planet in glaciers. It survived dramatic climate changes, ocean acidification, continental drift, all manner of catastrophes. Life finds a way, as a certain fictional scientist once said. Life is stubborn. Life persists. But losing the atmosphere, that might be asking too much, even of the most stubborn organisms. Let's start by thinking about the most obvious survival strategy: sealed environments. We've already talked about the International Space Station. They're fine, at least temporarily. They have oxygen, water recycling, food stores. They're already living in a sealed environment designed to keep humans alive in the vacuum of space. The loss of Earth's atmosphere doesn't change their immediate situation at all. From their perspective, nothing has changed except that Earth has stopped answering their calls. But their long-term prospects aren't great. They need resupply from Earth. Without anyone on Earth alive to launch rockets, they have maybe 6 months of consumables, maybe less if something breaks. The ISS is a marvel of engineering, but it's not designed for indefinite operation without support from Earth. It's a space station, not a generation ship. So they survive, but not forever. They'd be the last humans alive watching their home planet die beneath them, slowly running out of supplies, knowing there's no rescue coming. It's a profoundly lonely end. They might spend their remaining time trying to understand what happened, documenting everything, leaving a record for, well, for no one, since there's no one left to find it. But humans have this need to document, to explain, to leave something behind, even when we know it's futile. Submarines would have similar issues. A submarine that's submerged when the atmosphere disappears would be fine temporarily. Modern nuclear submarines can stay underwater for months without surfacing. They have sophisticated air recycling systems, food, water purification. The nuclear reactor provides power essentially indefinitely. Years, not months. They could theoretically outlast the ISS. A submarine crew could survive for months, maybe close to a year if they're very careful with their resources. They'd know something catastrophic happened when all communications went silent. They might surface briefly to investigate, just periscope depth, not opening hatches, and see the stars in the daytime sky. They'd figure out pretty quickly that the atmosphere is gone, but eventually they'd have to make a choice. They could stay submerged until their food ran out, or they could surface and face the vacuum. The submarine itself would be fine. Submarines are built to withstand enormous pressure differentials, and the pressure difference between 1 atmosphere and 0 atmospheres is nothing compared to the hundreds of atmospheres they're designed for. But the crew would need air, and there'd be none. So submarines. Yes, they survive longer than most, maybe longer than anything else with humans in it, but still not indefinitely. In the end, it's just choosing how to die. What about deep underground bunkers? This is where things get more interesting. If you have a sealed bunker deep underground, we're talking hundreds of feet or more, with its own life support systems, you could potentially survive for a long time, much longer than the ISS, much longer than submarines. The bunker would need air recycling. The most efficient way to do this is biological. Plants, especially fast-growing algae. You'd need hydroponics, grow lights, careful management of the carbon dioxide and oxygen balance. You'd need power, probably nuclear or geothermal since solar isn't an option underground, and you can't go outside to maintain surface equipment. You'd need water, which could be recycled. You'd need food, which you'd have to grow since stored food eventually runs out. The record for sealed environment survival is actually pretty good. Biosphere 2, that famous experiment in Arizona, kept 8 people alive for 2 years in a sealed environment. And that was more of a scientific experiment than a survival situation. They were testing concepts, not actually trying to survive. With better planning, better technology, lessons learned from that experiment, you could potentially extend that significantly. How long? Hard to say. Maybe years, maybe decades if everything worked perfectly and nothing broke. The Soviet Union built bunkers during the Cold War that were designed to sustain people for months or years after a nuclear war. Those principles would apply here. You'd need redundancy in critical systems, spare parts for everything, expertise to repair things when they broke. But indefinitely? Probably not. Eventually something critical would fail, or you'd run out of some resource you didn't think to stock, maybe trace elements needed for plant growth, maybe specific vitamins, maybe replacement parts for life support systems, or the psychological toll of living underground in a sealed box would become unbearable. And that psychological aspect is worth considering. Humans aren't built for long-term isolation in small spaces. We're social creatures, yes, but we also need variety, nature, the feeling of space around us. We need sunlight. Vitamin D deficiency is a real problem in sealed environments, and while you can supplement it, it's not quite the same. We need fresh air in a psychological sense. Even if the recycled air is chemically identical, we need the feeling of wind on our faces, rain, seasons changing, all those things that tell us we're alive in the world. Isolated in a bunker, knowing the surface is dead, knowing there's no escape, no relief, no possibility of going outside ever again. That would take a toll. Depression would be likely. Conflict would be likely. Humans under stress tend to argue. The social dynamics of a sealed environment are tricky. Who's in charge? Who makes decisions? What happens if someone becomes unstable? There have been studies on this, experiments with isolated groups, observations of Antarctic research stations during winter, data from submarines. The conclusions are pretty clear. Humans need psychological support, activities to stay mentally engaged, social structures that are fair and clear, and ideally, the knowledge that isolation is temporary. Take away that last part, the knowledge that you'll eventually get out, and things get much harder. So bunkers. Yes, they could sustain life for years, possibly decades with ideal conditions and perfect execution. But forever? Unlikely. The technical challenges are solvable. The psychological ones might not be. Now let's think about something more interesting from a biological perspective. Could any natural life survive? The surface is obviously out. No air means no surface life. Even extremophiles, organisms that survive in crazy conditions, need some conditions. They might not need much oxygen. They might survive extreme temperatures or extreme radiation. They might live in acid or in boiling water or in solid rock. But they need something, and the airless surface has nothing. It's vacuum, extreme temperature cycling, sterilizing radiation. Nothing survives that. But what about deep underground? Earth's crust goes down pretty far, miles and miles of rock, and within that crust, within the pores and cracks and fissures, there's life, bacterial life mostly. Archaea too, that third domain of life that's not quite bacteria, not quite anything else. Microbes that live in rock pores and groundwater in the spaces between mineral grains. They don't need sunlight. They're too deep to see any anyway. They don't need atmospheric oxygen. Many of them are anaerobes. They evolved before oxygen was common on Earth. They get their energy from chemical reactions with minerals, chemosynthesis instead of photosynthesis. They eat rock, essentially. Or rather, they metabolize the chemical energy released when certain minerals react with water or with each other. These deep biosphere organisms have been down there for millions of years. Some individual bacteria might be thousands of years old. Their metabolism is so slow, they divide so rarely, that time moves differently for them. They're isolated from the surface. They don't know or care what's happening up there. They're in their own little world of rock and mineral chemistry and darkness and timescales that make geological processes seem fast. Would they survive the loss of atmosphere? Probably yes, actually, at least for a very, very long time. The deep biosphere is protected by kilometers of rock. That's a lot of insulation. Temperature changes at the surface would take years, maybe thousands of years, to propagate down to where these organisms live. The rock conducts heat, but slowly, very slowly. Radiation doesn't penetrate kilometers of solid rock. Pressure changes at the surface wouldn't affect them. They're already under the pressure of all that rock above them, which is far greater than atmospheric pressure anyway. We're talking hundreds or thousands of atmospheres of pressure from the overlying rock. So the deep biosphere would be fine for years, for centuries, for thousands or millions of years possibly. But eventually things would change. The lack of atmosphere would affect the geochemistry of the surface. Water wouldn't cycle the way it used to. No rain means no infiltration of fresh water into the groundwater system. Minerals wouldn't weather the same way. Weathering requires water and atmospheric gases. These changes would, over long timescales, affect the chemistry of groundwater deep underground, which would affect the chemical reactions that deep biosphere organisms depend on for energy. It's hard to predict exactly what would happen. Geochemistry is complex, but over millions of years, the loss of atmosphere would probably affect even the deep biosphere. The system would change. Some organisms would die out. Some might adapt. Some might persist in isolated pockets where conditions remained favourable. So the deep biosphere might survive longer than anything else on Earth. Not because it's adapted to survive without atmosphere. It doesn't know about the atmosphere. It's never used it. It's never interacted with it. But because it's isolated from the surface, changes. It's in a different environment entirely, one that happens to be buffered from what's happening above. If we're looking for survivors on an airless Earth thousands or millions of years later, the deep biosphere is our best bet. Bacteria living miles underground, completely unaware that the surface world ever existed, going about their slow chemical business as they have for millions of years, and will continue to do for millions more. It's not the most exciting survival story. There's no drama, no heroism, no struggle against the odds, just bacteria doing what bacteria do, surviving because they happen to be in a place that's naturally isolated from the catastrophe above. They're the ultimate survivors, not through any special adaptation, but through sheer cosmic coincidence. They were in the right place when everything went wrong. Now let's think about something else. Could life recover? If the atmosphere somehow returned, would Earth come back to life? This is purely hypothetical. We're stacking impossible scenarios on top of each other at this point. But it's worth thinking about because it tells us something about what life needs. If the atmosphere returned quickly, within hours or days, before the water was completely lost, before the surface froze solid everywhere or boiled completely dry, then maybe there'd be a chance. The deep biosphere organisms would still be there. Some of them might make their way to the surface, the way they do through volcanic vents and hot springs now. With atmosphere and water returning, with temperature moderating, the conditions for life would exist again. But complex life, multicellular organisms, animals, plants, fungi, they'd all be gone, extinct, every last one, every species. You can't come back from suffocation and vacuum exposure and radiation damage, even if the atmosphere returned within hours, even if some cells survived in protected locations, the organisms they belong to would be dead. Dead is dead. Recovery would mean starting over from bacteria. It would mean evolution happening again, from single cells to multicellular organisms to, eventually, maybe, something complex. Earth did it once. Took about 3 billion years to get from the origin of life to complex multicellular organisms. Another billion years to get from simple multicellular life to the kind of complex ecosystems we see today. Would it happen again the same way? Maybe, maybe not. Evolution isn't deterministic. It's contingent on circumstances, on random mutations on which organisms happen to survive and reproduce. The second time might be completely different. Maybe no plants would evolve, maybe no animals. Maybe something entirely different would fill those niches. Or maybe nothing would. Maybe life would stay simple forever. But this assumes the atmosphere returned quickly. If weeks or months passed, Earth would lose most of its water. Water vapor would escape to space. The oceans would be gone. Continental ice would sublimate. Groundwater would gradually work its way to the surface and be lost. And without water, life can't exist. Even if the atmosphere returned, even if bacteria survived miles deep underground, they'd be stuck down there with no water to spread through. No way to colonize the surface. No way to evolve into anything more complex. Just bacteria in isolated pockets of groundwater, persisting as long as that water lasted, eventually dying out as it slowly escaped. An Earth without water is an Earth that stays dead, atmosphere or no atmosphere. Water is as essential as air, maybe more so. You can have anaerobic life, bacteria that don't need oxygen, but you can't have life without water. Not life as we know it, not life based on carbon chemistry. Water is the solvent, the medium, the environment where biochemistry happens. So recovery realistically requires the atmosphere to return almost immediately, before significant water is lost, which isn't going to happen in our scenario. In our impossible thought experiment, the atmosphere is gone, and it's staying gone. Let's talk about something that might seem strange, but comes up whenever people discuss survival in extreme conditions. What about tardigrades? Tardigrades, those microscopic creatures that look like tiny bears, sometimes called water bears or moss piglets, are famous for being nearly indestructible. They've become internet celebrities, actually. These little organisms that seem to survive anything. They can survive extreme temperatures near absolute zero and well above boiling. They can survive extreme pressure, 6 times deeper than the deepest ocean trench. They can survive radiation doses that would kill almost anything else. They can survive vacuum. They've survived exposure to space in actual experiments. They do this through a process called cryptobiosis, essentially drying themselves out and shutting down all metabolic processes. They expel almost all the water from their cells, produce protective molecules, and enter a state that's not quite alive and not quite dead. In that state, they can survive for years, decades, possibly centuries. So would tardigrades survive on an airless Earth? Maybe. For a while. It's complicated. Tardigrades can survive vacuum, yes. They can survive radiation, yes. But they can't survive indefinitely. Even in cryptobiosis, they eventually die. The state is protective, but not perfect. Radiation still damages their DNA, just more slowly. Chemical processes still occur, just much more slowly. Time still takes its toll. On the airless surface, tardigrades would face extreme radiation, UV and cosmic rays. They'd face temperature cycling that would stress their cellular structures even in the dormant state. They'd face micrometeorite impacts, slow sand blasting, all the hazards we've discussed. Most tardigrades would die quickly, hours or days, but some might survive longer, especially in protected spots, under rocks, in deep crevices, in places shielded from direct radiation and shaded from extreme temperature swings. Those might last months or even years. But they'd be stuck in cryptobiosis. They need water to revive. They need moisture to return to active life, to eat, to reproduce, to do any of the things that make them alive rather than just preserved. Without water, they stay dormant. They don't die immediately, but they don't live either. They just wait. And eventually, even dormant tardigrades die. Radiation damage accumulates. Molecular structures break down. The protection that cryptobiosis provides is impressive, but not infinite. Give it enough time, and even a tardigrade in cryptobiosis will degrade past the point of revival. So tardigrades, impressive survivors certainly. They'd outlast almost everything else, but not immortal. Not even close. They'd buy time, but time alone doesn't save you when the conditions for life are gone. What about bacterial spores? Some bacteria can form spores, essentially dormant armoured versions of themselves. A spore is like a seed, but even more hardcore. It's a bacterial cell that's shed most of its water, surrounded itself with protective layers, shut down its metabolism, and entered a state of suspended animation. Spores can survive extreme conditions. They've been revived from Arctic permafrost after thousands of years. They've been found in salt crystals millions of years old, though whether those were truly dormant that long or contamination is debated. They've survived in supposedly sterile environments, in vacuum, in radiation. They're incredibly tough. On an airless Earth, spores would face the same challenges as tardigrades. Radiation would damage them over time. Temperature cycling would stress them. But they're remarkably robust. Some spores in protected locations, deep in soil cracks, under rocks, in caves, might survive for years or even decades in a viable state. But like tardigrades, they'd need water to germinate. They'd need nutrients, suitable temperature, all the conditions necessary for life. An airless surface doesn't provide any of that, so they'd survive as spores, dormant and waiting, but they'd never become active bacteria again. They'd just sit there, slowly accumulating damage from radiation and temperature cycling, until eventually they were no longer viable, until the damage was too great for revival even if conditions improved. So survival on an airless Earth, when we really think it through, comes down to this. Isolated systems last longest. The ISS, submarines, bunkers. They survive as long as their supplies and life support last. Months to maybe a few years for the best prepared bunkers. The deep biosphere survives much longer, potentially millions of years, because it's genuinely isolated from surface conditions. Spores and tardigrades in protected spots survive for months to years, but in dormant states with no possibility of revival. But nothing on the surface survives long-term in an active living state. Life as we know it, complex, active, diverse life, ecosystems, food webs, all the beautiful complexity of the biosphere, is gone, stopped, ended. What's left is bacteria, miles deep underground, going about their slow business, unaware, and various dormant forms, spores, cryptobiotic organisms, waiting in the dark for conditions that will never come. It's a quiet end to the biosphere, not dramatic, not violent, just stopped, frozen in time, dormant, dead. And here's what's important to understand. This shows how essential the atmosphere is, not just for humans, not just for animals and plants, for all life everywhere on the surface and in the shallow subsurface. The atmosphere creates the conditions that make life possible. It provides the pressure that keeps water liquid, the protection from radiation, the temperature regulation, the medium for distributing heat and water. Everything. Remove it and life stops. Even the most resilient organisms can only wait it out for so long. Eventually time runs out. Resources deplete. Damage accumulates. Systems fail. We live in a delicate balance, an intricate system that looks stable because it's been stable for so long. But that stability requires maintenance. It requires the atmosphere to keep doing its job, day after day, year after year, billion years after billion years. Take it away, and the system collapses, quickly, completely, with very little hope of recovery. But remember, this is impossible. This won't happen. We're not going to lose our atmosphere. Earth's magnetic field protects it from solar wind. Gravity holds it down. It's been stable for billions of years and will be stable for billions more. We're safe. We're exploring this scenario to appreciate what we have. When you understand what it takes for life to survive, when you see how quickly it fails without the right conditions, you start to value those conditions. The air, the pressure, the protection, all of it. Take a breath. You can, because the atmosphere is there. We'll be there tomorrow. We'll be there for your children and grandchildren and thousands of generations beyond that. Life on Earth is resilient, yes, remarkably so, but only because Earth provides what life needs. The invisible ocean of air, the shield that stands between life and the void, the system that maintains the conditions that make the surface habitable. And we have it, right now, still there, still working. But for now, understand this. Survival without atmosphere is possible, but only in isolation, only in sealed systems, only temporarily. The surface becomes a place where nothing lives, nothing grows, nothing survives long-term. The atmosphere is what makes the difference between a living world and a dead one, between Earth as we know it and just another barren rock in space. So, we've explored survival, what little of it there is. Now let's look at what Earth becomes as time passes. Not just the first hours or days, but weeks, months, eventually years and beyond. What does a planet look like after it's lost its atmosphere? What changes happen over longer timescales? How does a living world transform into a dead one? We have a good example to look at, actually. Mars. Mars lost most of its atmosphere billions of years ago. It's been sitting there, airless and cold, for most of the history of the solar system. It's had time to settle into what an airless world looks like. It can teach us what Earth would become. But first, let's think about Earth in the weeks and months after losing its atmosphere. let's follow that transformation. The surface would be continuing to change. We've talked about the temperature extremes, the boiling and freezing water, the death of all surface life. But over weeks, those immediate, violent effects would settle into a new equilibrium. A harsh equilibrium, certainly. Extreme and hostile, but stable in its own way, predictable. The oceans would be mostly gone. Not completely. The deep ocean contains a lot of water, truly staggering amounts, and it takes time for all of it to boil or freeze and sublimate away. But the surface would be dry. Ocean basins would be exposed, full of salt deposits and sediment, but no water. Strange to look at from space. Continents and empty ocean basins, all the same dull colour. No blue anywhere. The defining characteristic of Earth, the water world, would be gone. You'd see the shapes of the ocean floor, the mid-ocean ridges, the trenches, the seamounts. All those features that are usually hidden under miles of water would be visible. The Mariana Trench would just be a trench. A very deep valley in the ocean floor, but not filled with water. You could walk into it if you had a spacesuit and walk down to the deepest point on Earth. No water pressure to contend with, just vacuum and temperature extremes. The atmosphere being gone means erosion stops, or rather, it changes dramatically. On Earth, with atmosphere, erosion is mostly about water and wind. Rain wears down mountains over millions of years. Rivers carve valleys. Wind shapes dunes and wears away rock. Ocean waves shape coastlines. All of that requires atmosphere, air for wind, air pressure for liquid water to exist. Without atmosphere, erosion still happens, but differently. Temperature cycling causes rocks to crack, thermal stress fracturing. We've talked about that. Meteorite impacts pit the surface, excavate craters. But there's no water to carve rivers, no wind to shape landscapes, no waves to erode coastlines. The geography that exists when the atmosphere disappears would largely remain frozen in time. Mountains would stay sharp. The jagged peaks wouldn't be rounded by weathering. Valleys carved by ancient rivers would stay exactly as they are. No river to deepen them, no rain to erode their sides. The landscapes that water created over millions of years would be preserved, like fossils, like photographs, a record of what Earth was when it had weather and water and life. The Grand Canyon would look exactly the same as it did the day the atmosphere disappeared. No Colorado River to carve it deeper, no rain to erode its walls, no wind to shift its dust. It would just stay forever, or at least for millions of years until something else changed it. Cities and human structures would be degrading. We've talked about this, but it's worth revisiting on these longer timescales. The temperature cycling would be brutal on materials. Day to night, night to day, 500-degree temperature swings every day. Concrete would crack, steel would fatigue, glass would shatter. Give it a year, and cities would look abandoned and deteriorating. Windows gone, roofs damaged, walls showing cracks, but still recognisably cities. The buildings would still be standing. Give it 10 years, and they'd look like ruins. Structural damage accumulating, materials failing, but the basic shape still visible. You could still tell what was a building, what was a bridge, what was a road. Give it 100 years, and they'd be significantly eroded by the slow sandblasting of micrometeorites. The constant rain of small impacts would be wearing away surfaces, pitting materials, gradually breaking things down. Buildings would be more damaged. Some might start to collapse from cumulative stress. Give it 1,000 years, and cities would be recognizable only as ruins. The shapes would still be there, foundations, the outlines of buildings, but heavily damaged, eroded, broken. But they'd erode slowly, much more slowly than on a planet with atmosphere and weather. There's no rust without oxygen and water, no biological decay without bacteria, no chemical weathering without water. Just physical stress, temperature cycling, radiation damage, occasional meteorite impacts. It's a slow degradation, measured in centuries and millennia rather than years. Ironically, the lack of atmosphere would preserve some things better than we preserve them now. Documents in buildings, protected from impacts and temperature extremes, might last thousands of years. Paper doesn't rot without bacteria and moisture. The Mona Lisa in the Louvre might still be recognizable after 1,000 years, though probably damaged by temperature cycling. Stone monuments like the pyramids might last millions of years. They're already resistant to weathering, and without water and wind, they'd endure almost indefinitely. The planet would be accumulating craters, small ones mostly from the constant rain of meteorites. Every piece of space dust, every pebble, every rock that normally burns up in the atmosphere hits the ground now. Most impacts are tiny, barely visible craters, but over years and decades they accumulate. Occasionally something larger hits, a boulder-sized meteorite, a small asteroid. These create obvious craters, nothing like the giant impact basins on the Moon. Those require truly enormous impacts, but significant, meters across, maybe tens of meters for a really big impact. Over years, the surface would become increasingly cratered. Not as heavily as the Moon has been collecting craters for 4 billion years, but noticeably, visibly from orbit, fresh, sharp-edged craters accumulating year by year. Let's think about what happens to ice, because Earth has ice caps, glaciers, frozen ground in permafrost regions, a lot of frozen water. What happens to all that ice without atmosphere? On the day side, ice exposed to direct sunlight would sublimate, turn directly from solid to vapor without passing through liquid. Melting requires pressure, and there's no pressure. The vapor would rise and escape to space. So sunlit ice disappears over days or weeks, depending on how thick the ice is. On the night side, ice would stay frozen. It's already frozen, and it would get even colder, hundreds of degrees below zero. But even in darkness, even at those extreme cold temperatures, ice slowly sublimates, very slowly. But over months and years, even nightside ice gradually turns to vapor and escapes. Ice buried under rock or soil would be protected longer. Temperature changes take time to penetrate through insulating layers of ground. But eventually, over years or decades, even buried ice would sublimate. The temperature cycling at the surface would gradually warm the subsurface, and buried ice would turn to vapor and work its way up through cracks and pores in the rock. So Earth's ice, the polar caps, the glaciers, the permafrost, all of it, would gradually disappear. Over weeks for surface ice in sunlight. Over months to years for surface ice in shadow. Over years to decades for deeply buried ice. The water vapor would escape to space. Earth would be losing mass, actually. All that water leaving means the planet is getting very slightly lighter. Not by much, but measurably, if you had precise enough instruments. The polar regions would be transformed. Antarctica, currently covered by ice kilometers thick, would become bare rock. The actual land surface of Antarctica would be visible for the first time in millions of years. The Arctic Ocean, currently covered by sea ice, would be an empty ocean basin. Greenland's ice sheet would be gone, revealing the rocky island beneath. These are landscapes we've never seen, not in human history, not in the entire history of human civilization. Ice has covered these places for millions of years. Their exposure would reveal geological features, rock formations, possibly fossils that have been hidden under ice for longer than our species has existed. Now let's talk about the magnetic field and radiation, because there's an interesting long-term interaction. Earth's magnetic field would still be working. The core is still molten, still churning, still generating the dynamo that creates the field. That field deflects charged particles from the solar wind, just like it always has. So in that sense, Earth is still protected from the worst of the solar wind's atmosphere stripping effects. But without atmosphere, the radiation that does make it through, UV from the sun, cosmic rays from deep space, charged particles that slip past the magnetic field, hits the surface directly. No ozone layer to absorb UV. No atmospheric molecules to collide with cosmic rays. Full-strength radiation reaching the ground. Over years and decades, this radiation would alter the chemistry of surface materials. UV light breaks chemical bonds. Cosmic rays create exotic isotopes. Radiation creates free radicals, highly reactive molecular fragments that then react with surrounding materials. The surface would start to look weathered, but in a way we're not used to. Not weathered by water and wind, but by radiation. Rocks would fade, change colour, develop what you might call a radiation patina. The colours would shift. Minerals at the surface would be altered by the constant bombardment of high-energy photons and particles. The surface would take on colours we don't normally see on Earth. Pinks and oranges and reds from iron oxides. Iron at the surface oxidizing slowly from reactions triggered by radiation. Greys and whites from radiation-modified minerals. Strange alien colours that would make Earth look less like itself and more like, well, more like Mars. It would start to look more like Mars, actually. Mars is red because its surface iron has oxidized over billions of years. Slow oxidation from whatever oxygen was produced by photodissociation of water in the thin atmosphere and from radiation-driven chemistry. Earth's surface would do something similar. The iron in rocks and soil would gradually oxidize. The planet would redden. Give it millions of years, and Earth might be quite red. The red planet, except it's Earth. A strange, unsettling transformation. Let's think about geological processes. What still works without atmosphere? Volcanism would still work. Volcanoes are driven by processes deep in the mantle, heat from radioactive decay, convection currents, melting of subducted crust. None of that requires atmosphere. If a volcano erupted on airless Earth, it would be strange to watch. If anyone were watching, which they wouldn't be, no explosive interaction with atmosphere to create ash clouds, no atmospheric moisture to create lahars, volcanic mud flows, just lava and volcanic gas venting into vacuum. The lava would behave differently. It would cool faster because there's no insulating atmosphere. The top surface would radiate heat directly to space and solidify quickly. But it would still flow. It would still create lava fields and shield volcanoes and all the features we associate with volcanism. The volcanic gases, water vapor, carbon dioxide, sulfur dioxide, would immediately expand into vacuum and escape to space. They wouldn't hang around to create a volcanic atmosphere, even temporarily. They'd just shoot up and out, gone. So volcanic eruptions wouldn't rebuild the atmosphere. They'd just lose Earth's interior volatiles to space. Earthquakes would still happen. Plate tectonics would still work. They're driven by heat from Earth's core and mantle, by the convection currents that move the plates. None of that requires atmosphere. Continental drift would continue. Mountains would still be uplifted by tectonic forces. Subduction zones would still operate, one plate sliding under another. But the surface expression would be different in one important way. On normal Earth with weather, mountains erode as fast as they're uplifted, more or less. There's an equilibrium. Tectonic forces push mountains up, and rain and ice and wind wear them down. The Himalayas are rising, but they're also eroding. They don't get much higher because erosion limits their height. Without erosion, mountains would build higher. They'd keep being uplifted by tectonic forces, but nothing would wear them down. Eventually, they'd reach an equilibrium where the weight of the mountain causes the rock to flow plastically at the base, kind of like how glaciers flow under their own weight. But that equilibrium is much higher than on a planet with erosion. So over millions of years, airless Earth would develop some truly enormous mountains, higher than Everest, higher than anything we have now. The landscape would become more dramatic, more extreme. Vertical relief would be measured in tens of kilometers, not just the 8 kilometers or so we have now. Tidal forces would still work. The moon would still orbit Earth, still raise tides, but without ocean water, you wouldn't see water tides. Instead, you'd have land tides, the solid body of Earth flexing slightly from the moon's gravity. This actually happens now, but we don't notice it because it's only a few inches, and the water tides are much more dramatic. On airless Earth, land tides would be the only tides. The ground beneath your feet, if you were standing there in a spacesuit, which you wouldn't be, would rise and fall by a few inches twice a day as the moon passed overhead. You'd never notice unless you had precise instruments. But it would happen, a subtle reminder that gravitational forces continue regardless of atmosphere. Over very long timescales, millions of years, the interaction between Earth and the moon would continue. The moon would gradually drift away, as it's been doing for billions of years and will continue to do. Earth's rotation would slow as the moon's tidal forces act as a brake. The day would get longer. All of this would happen whether there's atmosphere or not. These are gravitational processes, orbital mechanics, momentum transfer between Earth and moon. Now let's compare airless Earth to Mars, because the comparison is instructive and a bit sobering. Mars lost its atmosphere billions of years ago. Not all at once like in our scenario, but gradually over millions of years. It had rivers once, we're pretty sure. Maybe oceans. The evidence is debated but suggestive. Definitely lakes and groundwater. We can see the evidence carved into the landscape. Dry river valleys, ancient shorelines, deltas where rivers emptied into larger bodies of water, sediment deposits that only make sense if water was flowing. But Mars's core cooled. The core is smaller than Earth's, and smaller things cool faster. The magnetic dynamo stopped, the magnetic field disappeared, and over millions of years, with no magnetic protection, solar wind stripped most of the atmosphere away. Charged particles from the sun hit the upper atmosphere, transferred their energy to atmospheric molecules, and gave those molecules enough velocity to escape Mars's relatively weak gravity. What's left is a planet that looks like Earth might look after losing its atmosphere. Dry, cold, cratered, red from oxidation. Polar ice caps, water ice, and carbon dioxide ice. Ancient river valleys preserved because there's no erosion to erase them. Impact craters everywhere because there's no atmosphere to burn up meteorites. Sand dunes shaped by the thin wind that remains, but not much changed in millions of years. The main difference is that Mars has been like this for billions of years. It's had time for craters to accumulate, time for radiation to alter the entire surface, time for any remaining water to either escape or hide deep underground or freeze at the poles, time to settle into what an airless world looks like in equilibrium. Earth, even a year after losing its atmosphere, wouldn't look quite like Mars yet. It would still have the relatively fresh landscapes carved by recent water erosion. It wouldn't be as red. Radiation coloration takes time, thousands or millions of years. It wouldn't be as heavily cratered. Craters accumulate over millions of years. But the trajectory would be clear. The path would be obvious. Given time, given millions of years, Earth would become Mars-like. dry, cold, cratered, red. Another airless rock in space, bearing the marks of a past when water flowed and life existed, but no longer living, a museum of its former self. There's something sobering about that comparison. Mars used to be more like Earth, wetter, warmer, possibly habitable. Now, Earth, in our scenario, would be becoming more like Mars, dry, cold, definitely not habitable. The trajectory from living world to dead world, played out twice in the same solar system. One naturally, over billions of years. One artificially in our thought experiment, overnight. Let's think about what future visitors might find if there were any. If some alien civilization visited Earth 1 million years after it lost its atmosphere, what would they see? What story would they piece together? They'd see a cratered, airless world, red or reddish probably, dry. They'd see empty ocean basins full of salt deposits. They'd see river valleys and lake beds with no water in them, networks of channels that clearly carried water once but are bone dry now. They'd see volcanic features, shield volcanoes, lava fields, dormant but not eroded. They'd see the remains of cities, ruins by then, eroded by 1 million years of micrometeorite sandblasting and temperature cycling, but still recognizable as artificial structures. The grid patterns of streets, the foundations of buildings, possibly some structures still partially standing, though heavily damaged. They'd see fossils, lots of fossils. All the life that died when the atmosphere was lost would be preserved in many places, without bacteria to decompose them, without water to wash them away, without oxygen to let them decay. Many corpses would just stay there, dried out, mummified. Over time, micrometeorites would gradually destroy surface remains, but things buried in sediment or protected in caves might survive. It would be like the ultimate fossil record, a snapshot of an entire biosphere, all dying at the same moment, all preserved in the state they were in when it happened. It would tell a story, the story of a living planet that lost its atmosphere and died. They'd find fossils of humans, actually, alongside fossils of everything else. Our cities would tell them we were technological. Our bodies would tell them we were mammals, primates specifically. The fossil record would be remarkably complete. They might find our satellites still in orbit. Satellites don't need atmosphere. They orbit above it anyway. They'd be damaged by 1 million years of radiation and micrometeorite impacts, but they'd still be up there, dead, dark, non-functional but still orbiting. The International Space Station, GPS satellites, communication satellites, the James Webb Space Telescope, all still up there, silent monuments to a civilization that built them. They might find the rovers we sent to Mars. A nice irony. By the time these alien visitors arrive, Earth and Mars would both be airless and similar looking, and Mars would have Earth's rovers sitting on its surface while Earth had none. The aliens might wonder why Earth sent machines to Mars when both planets ended up in similar states. They wouldn't know that Mars was already airless when we sent the rovers, that we were studying Mars to understand planetary atmospheres and climate. They'd probably conclude pretty quickly that something catastrophic happened. The evidence would be clear. A planet that clearly had liquid water, clearly had life, clearly even had technological civilization, now airless and dead. All the life forms dead at the same time. Same layer in the geological record, same moment in time. Something sudden happened here. They'd write papers about it, or the alien equivalent of papers. They'd debate what could cause such rapid loss of atmosphere. They'd probably conclude it was a mystery, because it is a mystery. There's no known natural mechanism for Earth to lose its atmosphere this quickly. It would be genuinely puzzling. A planet that should be fine, that has all the characteristics necessary to keep its atmosphere, somehow lost it. They'd be confused, as they should be. But let's return to our thought experiment, to our impossible scenario. Let's think about much longer timescales. Not just thousands or millions of years, but tens or hundreds of millions of years. What would Earth be like then? The surface would be heavily cratered. Hundreds of millions of years of meteorite impacts would accumulate. It wouldn't be as cratered as the Moon. The Moon is 4 billion years old and has been collecting craters all that time. But Earth would be significantly more cratered than it is now. Craters upon craters, overlapping, new ones obliterating old ones, the surface telling a story of constant bombardment. All traces of recent life would be gone from the surface. Fossils in rock would remain, protected by burial. But anything organic on the surface would be destroyed by radiation, impacts, temperature cycling. The mummified remains would be broken apart, scattered, erased. Only fossils preserved in sedimentary rock, buried and protected, would survive this long. Cities would be heavily eroded, barely recognizable. Some foundations might still be visible. Hard bedrock doesn't erode quickly, even over millions of years. But buildings, structures, anything made of materials less durable than solid rock would be mostly gone. You'd have to know what to look for to recognize the ruins as artificial. The landscape would be more dramatic than Earth has ever been. Mountains impossibly high, built up by tens of millions of years of tectonic uplift, with no erosion to wear them down. Rift valleys possibly deeper than the Mariana Trench is now. The vertical relief on the planet would be extreme. The planet would be red, thoroughly red. Billions of tons of surface iron oxidized over millions of years, altered by radiation, weathered in that strange radiation-driven way. The characteristic rust-red color of Mars would have developed on Earth too. Maybe not exactly the same shade, different starting minerals, different conditions, but red nonetheless. The red planet and the red planet, two worlds that once were very different, now similar in their airlessness and death. And it would be quiet, completely, utterly quiet. No sound at all. Sound requires a medium, and there's no medium. No life. No geological activity you could hear even if there were air. Just a dead world, slowly accumulating craters, slowly being altered by radiation and temperature cycling, slowly becoming more and more difficult to recognize as Earth. It's a melancholy picture, not dramatic, not violent, just empty, silent, dead, a world that once was alive, that once was home to billions of organisms and an entire biosphere, now just rock and radiation and vacuum. But here's what's important to remember, what we keep coming back to. This won't happen. Earth's atmosphere is stable, has been for billions of years, will be for billions more. The magnetic field protects it. Gravity holds it down. The core is still hot, still generating that protective field. There's no mechanism for rapid atmospheric loss. Mars lost its atmosphere because its core cooled, but Earth's core will stay hot for billions of years, so long that the sun will have evolved into a red giant and destroyed the inner planets before Earth's core cools enough to matter. We're safe. The atmosphere isn't going anywhere. We've talked about Mars several times now. We've used it as a comparison, as an example of what Earth would become. But let's look at Mars more closely. Because Mars isn't just a hypothetical, it's real. It's out there right now, about 140 million miles away on average, sometimes closer, sometimes farther, as our orbits carry us. And its story is worth understanding. Mars used to have an atmosphere, a thick one. We're increasingly certain of this. The evidence is carved into the landscape. When you look at high-resolution images of Mars, and we have truly extraordinary images now, from orbit and from rovers on the surface, images so detailed you can see individual rocks. You see features that only make sense if water was flowing, lots of water, for a long time. River valleys, complete with tributary systems feeding into main channels, exactly like river systems on Earth. Lake beds with ancient shorelines you can still see, elevation changes marking where water once lapped against ancient shores, deltas where rivers emptied into larger bodies of water, depositing sediment in fan-shaped formations exactly like river deltas on Earth, the Mississippi Delta, the Nile Delta, except on Mars and now dry, canyon systems that look like they were carved by catastrophic floods, massive channels that could only have been created by enormous volumes of rushing water. And it's not just one or two features, it's everywhere. Mars's surface is covered with evidence of ancient water. The geological record is clear. Water doesn't flow without atmosphere, or rather, liquid water doesn't exist without atmospheric pressure. We've talked about this. Without pressure, water either boils or freezes. It can't stay liquid. There's no comfortable middle ground. So if Mars had flowing water, if it had rivers and lakes and possibly even an ocean, it must have had enough atmospheric pressure to keep that water liquid. How thick was Mars's atmosphere? We're not completely sure. Estimates vary based on different models and assumptions, but probably at least comparable to Earth's atmosphere, possibly even thicker. Enough for liquid water to exist on the surface, enough for a water cycle, evaporation, clouds, precipitation, enough for weather, enough, perhaps, for Mars to have been habitable. We don't know if Mars ever had life. We're looking for evidence. That's partly why we send rovers there. They're designed to search for signs of ancient life, biosignatures in rocks, organic molecules, anything that might tell us life existed there. We haven't found definitive proof yet. We've found organic molecules, but those could have non-biological origins. We've found methane in the atmosphere, which is interesting, because methane doesn't last long in Mars's atmosphere. It gets broken down by UV radiation, so something must be producing it. But we don't know what. Could be biological, could be geological. We're still looking. But the conditions seem like they were right, at least for a while. Mars had water, it had a thicker atmosphere, it was warmer, had to be for liquid water to exist. It might have had the conditions necessary for life to emerge. And then it lost its atmosphere. Not suddenly, not overnight like in our thought experiment about Earth gradually over millions of years. But the result was the same, a planet that went from potentially habitable to definitely not habitable. From a world that might have hosted life to a world that definitely doesn't now. Here's what we think happened based on decades of observations, measurements from spacecraft, data from rovers, and computer modelling of atmospheric processes. Mars formed about the same time as Earth, about 4.5 billion years ago, from the same disk of dust and gas that formed the Sun and all the planets. It started hot. Everything starts hot when you're assembling a planet from colliding rocks. It had a molten core, just like Earth. That core generated a magnetic field through the dynamo effect, the same process that generates Earth's field. Charged molten iron rotating in the presence of an existing field generates more magnetic field. It's a self-sustaining process, as long as the core stays hot enough to remain molten and convection keeps it stirring. That magnetic field protected Mars's atmosphere from the solar wind, just like Earth's magnetic field protects Earth's atmosphere. The charged particles streaming from the Sun would hit the magnetic field and be deflected around the planet. They'd flow around Mars like water flowing around a rock in a stream. The atmosphere was safe, shielded, protected. But Mars has a problem that Earth doesn't have. It's smaller. about half Earth's diameter, about 11% of Earth's mass, and smaller things cool faster. It's a surface area to volume issue. Heat radiates from the surface, but heat capacity depends on volume. Smaller objects have more surface area relative to their volume, so they lose heat faster relative to how much heat they can store. You can see this with baked potatoes, actually. If you bake a small potato and a large potato at the same temperature, then take them out of the oven. The small potato cools faster. Same principle applies to planets. Mars is the small potato. Earth is the large potato. Both started hot. Mars cooled faster. Mars's core cooled. Not all the way. The interior of Mars is still hot, still partially molten, but enough that the convection currents in the molten outer core slowed down, became less vigorous. The dynamo weakened, and somewhere around 4 billion years ago, maybe a bit earlier, the magnetic field failed completely. It didn't gradually weaken. The geological evidence suggests it shut off relatively suddenly, at least in geological terms, over maybe a few million years, which is sudden for planetary processes. We know this happened because ancient rocks on Mars show remnant magnetization. They were magnetized when Mars had a field, and they've held onto that magnetization for billions of years, like fossils of a magnetic field that once existed. But younger rocks aren't magnetized. There's a clear division in the geological record between the time when Mars had a magnetic field and the time when it didn't. The field turned off, and from that point forward, rocks formed without being magnetized. Without the magnetic field, Mars's atmosphere was vulnerable. The solar wind, no longer deflected by a protective magnetic bubble, hit the upper atmosphere directly. Charged particles, mostly protons and electrons, but also alpha particles and heavier ions, collided with atmospheric molecules. These collisions are energetic. When a charged particle moving at hundreds of kilometers per second hits an atmospheric molecule, things happen. Some of those collisions transferred enough energy to atmospheric molecules to give them escape velocity. They'd gain enough speed to overcome Mars's gravity, which is weaker than Earth's gravity because Mars is less massive, and drift off into space. Not immediately. Not like a rocket launch. But gradually. The molecule would be knocked upward, gaining altitude, and if it didn't collide with another molecule and lose that energy, it would eventually reach the edge of the atmosphere and escape. This is called atmospheric sputtering. It's a slow process. You don't lose your atmosphere overnight, but year after year, century after century, million years after million years, Mars bled air into space, molecule by molecule, atom by atom. The solar wind was steadily eroding the atmosphere. And once the process started, it accelerated in a way. As the atmosphere thinned, the pressure dropped. As the pressure dropped, water couldn't stay liquid. Lakes dried up. Rivers stopped flowing. The water cycle broke down. Some water evaporated and then was lost to space. Water vapor molecules got hit by solar wind, split apart by UV radiation, and the hydrogen escaped while the oxygen either escaped or combined with rocks to form oxides. As water was lost, Mars dried out. As Mars dried out, the greenhouse effect weakened. Less water vapor, less CO2 from a thinner atmosphere. As the greenhouse effect weakened, temperatures dropped. As temperatures dropped, remaining water froze. As water froze, it could no longer participate in the water cycle, couldn't evaporate to form clouds, couldn't fall as rain. The climate system collapsed. How long did this take? We're not entirely sure, but current models suggest tens to hundreds of millions of years. The magnetic field shut off around 4 billion years ago. The atmosphere was probably mostly gone by 3.5 billion years ago, though remnants persisted longer, so maybe 500 million years, to go from thick atmosphere to thin atmosphere. Maybe a bit less, maybe a bit more. Not fast on a human timescale, not even fast on the timescale of biological evolution, but fast on a geological timescale. Mars went from potentially habitable to definitely not habitable in a relatively short period of planetary history, a tenth of the age of the solar system, a blink, cosmically speaking. What's left now is a thin atmosphere, less than 1% the pressure of Earth's atmosphere, about 0.6% to be precise. Mostly carbon dioxide, 95% CO2, with a bit of nitrogen and argon and traces of other gases. So thin that liquid water can't exist on the surface. It would either boil or freeze. So thin that it barely provides any protection from radiation or meteorites. You could stand on Mars's surface and see stars in the daytime because there's not enough air to scatter the light and make the sky blue. Mars still has an atmosphere, technically, but for all practical purposes, it's airless. The atmospheric pressure on Mars is roughly equivalent to the pressure at 100,000 feet altitude on Earth. That's well above the Armstrong limit, the altitude where water boils at body temperature. Spacesuits are required. You can't breathe it, not just because it's CO2, but because there's not enough of it. Your lungs wouldn't function at that pressure, even if it were pure oxygen. And here's what's interesting, and a little unsettling when you think about it. This could happen to Earth. Not tomorrow, not any time soon, not for billions of years. But eventually, on a long enough timescale, Earth's core will cool, just like Mars's did. The magnetic field will weaken and eventually fail. And when that happens, Earth's atmosphere will be vulnerable to the same solar wind stripping that stripped Mars's atmosphere. The timescale is important here, and it's worth being clear about. Earth's core is much larger than Mars's core. It contains much more thermal energy. It will take much, much longer to cool. Current estimates, based on models of heat flow, radioactive decay, and core composition, suggest Earth's core might cool enough for the magnetic field to fail in about 5 billion years. Maybe longer. Possibly as much as 10 billion years. But here's the thing. The Sun will become a red giant in about 5 billion years. As it exhausts the hydrogen in its core, it will start fusing hydrogen in a shell around the core, and this will cause it to expand dramatically. It will swell up, becoming larger and cooler at the surface, but much brighter overall. It will probably engulf Mercury and Venus. It might reach Earth's orbit. Current models are uncertain about whether Earth will be swallowed or will survive just outside the Sun's expanded surface. So Earth might be destroyed by the Sun's expansion before its magnetic field fails, which is weirdly comforting, in a dark humour sort of way, like being told you'll die of heart disease before the cancer gets you. It's still dying, but at least you don't have to worry about both. But the principle remains. Magnetic fields are important. They protect atmospheres. Without them, rocky planets in the inner solar system, close enough to the Sun that the solar wind is strong, lose their air over geological time. Mars proves this. Venus is an exception we'll discuss in a moment, but Mars is the typical case. This isn't speculation or theory, it's observation. It happened. We can see the evidence. Venus is an interesting comparison here, because Venus complicates the picture. Venus also doesn't have a strong magnetic field. Its core either never generated a vigorous dynamo, or it stopped long ago. We're not sure which. But Venus still has an atmosphere. A very thick atmosphere, 90 times denser than Earth's. Thick enough to crush spacecraft on the surface. Why? Several factors. Venus is more massive than Mars, about 81% of Earth's mass compared to Mars's 11%. That stronger gravity helps hold onto atmosphere. Venus is also closer to the Sun, which seems like it would make atmospheric loss worse, but actually helps in a counterintuitive way. The upper atmosphere gets heated more by solar radiation, which causes it to expand. A more expanded atmosphere is actually harder to strip away. The molecules are more spread out. Collisions between solar wind particles and atmospheric molecules are less efficient. Also, Venus's atmosphere is so thick and so rich in CO2 that even if it's losing atmosphere at the top, the rate is very slow compared to the total amount of atmosphere. It would take billions of years to strip Venus's atmosphere even without a magnetic field. So Venus kept its atmosphere despite lacking a magnetic field. But Venus is a special case, more massive than Mars, closer to the Sun, really thick atmosphere to start with. Mars is more typical of what happens to small rocky planets without magnetic fields. They lose their air. Earth, with its magnetic field, is protected. But remove that field, and Earth would be more like Mars than like Venus. The Mars missions over the past few decades have taught us a tremendous amount about atmospheric loss. The MAVEN spacecraft, Mars atmosphere and volatile evolution, has been orbiting Mars since 2014, specifically studying how Mars loses atmosphere to space right now. Not billions of years ago, but today. In real time, it measures the rate of atmospheric escape, studies how the solar wind interacts with Mars's ionosphere, watches how solar storms affect the loss rate. What MAVEN found is that Mars is still losing atmosphere right now, today. The process hasn't stopped just because the atmosphere is already thin. About 100 grams per second escapes, mostly hydrogen and oxygen, the lightest components. That sounds like a lot, but it's actually tiny compared to the remaining atmosphere, which has a mass of about 25 trillion kilograms. At the current rate, it would take billions of years to strip what's left. But the lesson is clear. Without a magnetic field, atmospheres leak. Slowly, persistently, inexorably. Given enough time, they're lost. Mars is a warning. It's not a cautionary tale in the sense that we need to panic, but it's instructive. It shows us what can happen to a planet that loses its magnetic field. It's not an impossible scenario or a hypothetical. It's a real outcome that happened to a real planet in our own solar system. Earth is protected for now, well protected, and will be for billions of years. But that protection depends on our magnetic field continuing to work. As long as the core stays hot and the dynamo runs, we're fine. But magnetic fields aren't guaranteed forever. There's something sobering about looking at Mars and seeing Earth's possible distant future. Billions of years from now, if Earth somehow survives the Sun's red giant phase, maybe we've moved it to a farther orbit, maybe the Sun's expansion is less than predicted, maybe something else happens. Earth might look like Mars, dry, cold, airless, red. The magnetic field failed. The atmosphere slowly escaped. Water was lost. Life ended. It's not something to worry about in any practical sense. We have billions of years. Billions. That's longer than complex life has existed on Earth so far. Complex life is only about 600 million years old. It's longer than Earth itself has been recognizable as Earth in its current form. It's an almost incomprehensibly long time. But it's a reminder that planets change. Habitability isn't permanent. What's a living world now might not be a living world forever. Mars was probably habitable once for hundreds of millions of years. Now it's not, and hasn't been for billions of years. Earth is habitable now, but on a long enough timescale that could change too. Does this mean we should worry? No, not about this. We have more immediate concerns. Climate change that's happening now, asteroid impacts that could happen any time, pandemics, nuclear war, things that could happen on human timescales that we actually need to deal with. The magnetic field failing is so far in the future that it's purely academic, a curiosity, something interesting to think about, but not something to lose sleep over. But Mars teaches us to appreciate what we have, a working magnetic field that's been protecting us for billions of years and will continue to do so for billions more. A stable atmosphere held in place by that field and by gravity, the right-sized planet, big enough to hold atmosphere, small enough that the core will stay hot longer than the sun will stay stable. The conditions for life. We're in a sweet spot, cosmically speaking. Not too hot, not too cold, not too close to the sun, not too far. The right size, the right magnetic field, the right atmosphere, the right distance from a star of the right size and age. Mars had some of these things once, but lost them. It's a cautionary tale, but not a call to panic. More like a reminder to value what we have while we have it, to appreciate the invisible shields that protect us, to understand that habitability isn't guaranteed forever, even if not forever means not for billions of years. Take a breath. You can, because Earth still has its atmosphere, still has its magnetic field, still has all the conditions necessary for life. Mars can't offer you that breath anymore. Its air is too thin, too cold, too inhospitable. The pressure is too low. The temperature is too extreme. You'd need a spacesuit to survive there. But Earth can. Earth does. Every breath you take is possible because of that invisible shield, that magnetic field and atmosphere working together to keep you alive. Mars lost that. Earth hasn't, and that makes all the difference. So, we've seen what happens when Earth loses its atmosphere. We've explored Mars as an example of a planet that actually did. Now let's think about something more practical, if practical is the right word for this scenario. What would it take to live without atmosphere? Not just survive for a few hours or days, but actually live. Maintain a human presence. Keep civilization going in some form, however diminished. What would the engineering look like? What would daily life be like? What would it mean to be human on an airless Earth? It's worth exploring because, in a way, we already know how to do this. We have people living in space right now. The International Space Station is essentially a habitat in an airless environment. Submarines operate sealed from their surroundings. We've built Antarctic research stations that are partially isolated from the hostile environment outside. We have the technology. The question is, could we scale it up? Could we sustain it indefinitely? And perhaps more importantly, would we want to? Let's start with the basics. What would you need to survive on an airless Earth? First, and most obviously, air to breathe. Oxygen specifically. Humans need about 550 litres of oxygen per day. That's roughly 0.84 kilograms. Not a huge amount, but it needs to be constantly replenished because we convert it to CO2 with every breath. The best way to provide air is recycling. The ISS does this right now. They have systems that remove CO2 from the air, using lithium hydroxide canisters or more advanced molecular sieves and chemical scrubbers. They have systems that split water into hydrogen and oxygen through electrolysis. The oxygen goes back into the air for breathing. The hydrogen is either vented or combined with CO2 to make water and methane through the Sabatier reaction. It's a closed loop, more or less. Not perfectly closed. You lose some air through leaks, through airlocks when people go outside, through inefficiencies in the system, but you can recycle most of it. The ISS gets resupply shipments that include oxygen tanks, but they could theoretically go longer without them if they had to. For a habitat on airless Earth, you'd need similar systems: air recyclers, CO2 scrubbers, water electrolysis for oxygen generation. These are proven technologies. We know they work. We've tested them for years in space. The question is maintenance and reliability over years or decades rather than months. Can you keep them running indefinitely? What happens when parts wear out? Second, water. Humans need about 2 litres per day for drinking, more for sanitation, hygiene and food preparation. Ideally 4 to 5 litres per person per day for comfortable living. Again, recycling is key. The ISS recycles urine and humidity condensation, the moisture that collects on cold surfaces, back into drinking water. It's not pleasant to think about, but it works. The water is heavily filtered, distilled, purified, tastes fine. Astronauts joke that today's coffee is tomorrow's coffee, which is technically accurate and somehow both funny and slightly disturbing. On airless Earth, you'd have the advantage that water might still exist underground, at least initially. You could potentially mine ice deposits or tap into deep aquifers if you're far enough down that the water hasn't sublimated yet, but surface water would be gone, so you'd need to either bring your water supply with you into the habitat or find it underground and pump it in, and then recycle it obsessively. Every drop matters. You can't afford to waste water when there's no rain to replenish it. Third, food. This is trickier than air or water. You can't just grow crops on the surface. No air, no water, extreme temperatures, deadly radiation. Everything has to be indoors, in controlled environments. Hydroponics would be your best option. Growing plants in nutrient solution without soil. Controlled environment agriculture. You'd need grow lights, probably LEDs because they're energy efficient, and you can tune them to the specific wavelengths plants need for photosynthesis. You'd need careful control of temperature, humidity, CO2 levels. Plants actually need more CO2 than atmospheric concentration for optimal growth, so you'd pump some of that CO2 you're scrubbing from the air into the greenhouses. You'd need to pollinate plants manually since there are no bees or wind to do it naturally. The ISS has experiments with growing food. They've successfully grown lettuce, radishes, some herbs, even a few flowers. But they're not self-sufficient, not even close. They grow small amounts for fresh food and morale. For full nutrition, you'd need a much larger growing area and much more variety of crops. How much space do you need to feed one person? Estimates vary depending on diet and efficiency, but roughly 50 to 100 square meters of growing space per person for a complete nutritionally adequate diet. That's a lot. For 100 people, you'd need an entire greenhouse complex, multiple growing chambers, thousands of square meters, and you'd need to close the loop here too. Human waste would need to be composted or chemically broken down and used as nutrients for plants. The nitrogen cycle, the carbon cycle, the phosphorus cycle, all the cycles that normally happen across Earth's entire biosphere would need to be managed artificially in your little habitat. It's possible, but it requires constant attention and careful management. Fourth, energy. You need power for everything. Air recycling, water purification, grow lights, heating, cooling, air circulation, life support computers, medical equipment, lighting, communications. A lot of power. A typical person in a modern developed country uses about 11,000 kilowatt hours per year. In a habitat, you might be more efficient, but you'd still need several kilowatts per person continuously. Solar panels would work on airless Earth. Actually, they'd work better in some ways. No atmospheric absorption of sunlight, so you get full intensity solar radiation, maximum efficiency, but you'd have the problem of night. Earth still rotates. Half the time, you're in darkness. You'd need battery storage or some other way to provide power during the night. And batteries are heavy, expensive, and wear out over time. Nuclear power would be better for a permanent installation. A small modular reactor could provide constant power for years, even decades. This is actually one of the leading concepts for Mars bases. Bring a nuclear reactor, bury it for radiation shielding, run everything off that. The technology exists. We've used nuclear reactors in submarines for decades. Scaling it down for a habitat is engineering, not science fiction. Geothermal might work if you're in the right location. Earth's interior is still hot. Drill down far enough and you can tap into heat. Use it directly for heating, or use it to generate electricity. Iceland does this now with their volcanic activity. On airless Earth, you just need to drill deeper to reach the heat. Fifth, pressure. This is non-negotiable. Humans need atmospheric pressure around our bodies. The habitat has to be sealed and pressurized to roughly Earth normal pressure, about 14.7 pounds per square inch. This means your habitat is essentially a pressure vessel, like a submarine or a spacecraft. Every wall, every floor, every ceiling, every window is holding back vacuum. Any leak is potentially catastrophic. You'd need multiple layers of redundancy, double walls with monitoring of the space between them to detect leaks early, emergency patches ready at all times, constant monitoring for pressure drops, alarms set to alert if pressure falls even slightly. Airlocks would be essential. You can't just open a door to the outside. That would vent all your air into the vacuum in seconds. Every entrance and exit needs to be an airlock. 2 doors with a chamber between them. You enter the chamber, close the first door, evacuate the air from the chamber, then open the second door to the outside. To come back in, you reverse the process. It's slow, but necessary. Every trip outside requires this procedure. Sixth, temperature control. Without atmosphere, temperatures are extreme and they cycle dramatically. You'd need excellent insulation to protect against the temperature swings outside. Thick walls, multiple layers of insulation. Possibly underground construction. Rock is a good insulator, and going underground protects you from temperature extremes and radiation simultaneously. You'd need heating for when you're in shadow, cooling for when you're in sunlight. Heat management would be a constant engineering challenge. During the day, you'd need to reject heat, radiators on the surface to dump excess thermal energy. During the night, you'd need to conserve heat, shut those radiators, insulate, maybe use stored heat or active heating. Seventh, radiation shielding. UV radiation from the sun, cosmic rays from deep space, solar particle events during solar storms. Without atmosphere to block them, they hit the surface at full strength. Long-term exposure causes cancer, damages DNA, weakens the immune system, increases the risk of cataracts. It's not immediately lethal, but over months and years, it's very dangerous. The solution is shielding, mass between you and the radiation, thick walls made of heavy materials, concrete, regolith, lead, water, rock, or go underground. Even a few meters of rock provides excellent radiation shielding. Water is actually great for radiation shielding. Hydrogen atoms are effective at stopping both neutrons and charged particles. And you need water anyway, so you might design your habitat with water tanks forming part of the walls. Dual purpose, radiation shield and water storage, clever engineering. Eighth, psychological needs. This is often overlooked in engineering discussions, but it's absolutely critical for long-term survival. Humans aren't built to live in small enclosed spaces indefinitely. We evolved in wide-open environments. We need space, variety, nature, social interaction, meaningful work, and the feeling that we're more than just surviving. Your habitat would need to be as spacious as resources allow, ceilings high enough not to feel claustrophobic, common areas for social gathering, private spaces for solitude and personal time, windows, small, heavily shielded, probably triple-paned, but windows, views, even if the view is of a barren, hostile landscape, it's psychologically important to see outside. Art would be important. Colour, decoration, variety in the environment, not just sterile white walls and metal surfaces. Green growing spaces. Plants are psychologically beneficial even beyond their function as food. The colour green, the smell of growing things, the feeling of tending something alive, all of these matter for mental health. You'd need social structures that work, clear leadership that's seen as fair, systems for making decisions that everyone accepts, ways to resolve conflicts peacefully. Isolated groups under stress tend to develop social problems. We've seen this in Antarctic stations, in isolated communities, in long-term experiments. You'd need to design for this, possibly rotation of leadership, democratic decision-making, clear rules everyone agrees to. Recreation would be essential. Exercise equipment. You'd need to stay healthy. Books, movies, games, hobbies, ways to learn new skills, education for children, ways to stay mentally engaged and stimulated. The best habitats would feel less like survival shelters and more like homes, more like communities where people can actually live rather than just not die. So, let's put this together. What does a functional long-term habitat on airless Earth actually look like? Probably underground, at least partially. This gives you natural temperature stability, radiation shielding, and protection from meteorites. You'd have a surface structure for solar panels, possibly greenhouses with transparent roofs and heavy radiation shielding, airlocks for accessing the surface. Underground, you'd have living quarters, private rooms for individuals or families, communal spaces for gathering, life support machinery rooms, air recyclers, water purifiers, power systems, hydroponic gardens, multiple chambers for different crops, water storage tanks, food storage for dried goods and emergencies, workshops for maintenance and manufacturing, medical facilities, recreation areas, libraries or computer rooms, everything a small community needs to function. Population-wise, you probably want at least a few hundred people, maybe 1,000 for a sustainable community. Too few and you have genetic bottleneck problems over generations. Too few and you don't have enough specialized skills to maintain all the systems. Too many and resource demands become difficult to meet, especially food and water. This is very similar to concepts for Mars colonies, actually. It's almost identical. Living on airless Earth would be like living on Mars, except with Earth gravity instead of Mars's 38% gravity, which is actually a significant advantage. Your bones and muscles wouldn't atrophy. Your cardiovascular system would work normally. Children could develop normally. Gravity is good for human bodies. How long could you maintain this kind of habitat? Decades, certainly, if you designed it well. Maybe centuries if everything was maintained carefully and nothing catastrophic happened. But indefinitely? That's much harder to say. The engineering challenges are solvable. We have the technology. But there are long-term problems that are harder to address. System failures are inevitable. Eventually something breaks. A pump fails. A seal cracks. An electronic component dies. Do you have replacements? Can you manufacture new parts? Metals and plastics require complex industrial processes. Can you maintain that industrial base with a population of hundreds or thousands? The ISS has this problem constantly. When something breaks, they either fix it with whatever they have on hand, or they wait for the next resupply mission to bring new parts. On airless Earth, there are no resupply missions. You have what you have. You need to be able to make or repair everything yourselves. You'd need manufacturing capability. mining and refining raw materials, smelting metals, making plastics, producing electronics, manufacturing tools, parts, components. That's a vast amount of industrial infrastructure for a small population to maintain. Can 1,000 people support all of that? Then there's the knowledge problem. Can a population of 1,000 people maintain all the specialised knowledge necessary to run and repair complex life support systems? You'd need engineers, technicians, doctors, farmers, teachers, maintenance workers, a lot of specialised knowledge distributed across many people. If key people die or don't successfully pass on their knowledge to the next generation, critical systems fail. And the genetic diversity problem. 1,000 people is probably enough to avoid severe inbreeding problems for several generations. But long-term, over centuries, you'd start to see genetic issues accumulating. You'd need genetic diversity to maintain a healthy population. Ideally, you'd want tens of thousands of people, not hundreds or thousands. Anything less is a long-term risk. So realistically, a habitat on airless Earth could sustain human life for decades to maybe a century or two. Beyond that, you'd start facing serious challenges that would be difficult to overcome without a much larger population and industrial base. It's survivable, yes. Humans could persist, but it's not really thriving. It's existence, not life in the full sense. You're maintaining a presence, preserving the species, but at what cost? Confined to sealed habitats forever, no ability to go outside without a spacesuit, no open sky, no rain on your face, no wind in your hair, no ocean to swim in, no forest to walk through, no natural environment at all. Just artificial everything, all the time. Temperature controlled, air filtered, water recycled, food grown under lights. Every aspect of your environment managed by technology. Compare this to what we have now, right now. Step outside. You can, anytime you want. Feel the breeze. Breathe freely without thinking about it. Look up at the sky, blue during the day, stars at night. Feel rain on your face, snow on your hands. Walk barefoot on grass, swim in a lake, climb a mountain, watch the sunset. Listen to birds, smell flowers. These are things we take completely for granted. Things we barely notice because they're always there. On airless Earth, none of that exists anymore. Outside is death. The surface is hostile. You live in a box, and you stay in the box, and the box is your entire world. You might go outside in a spacesuit occasionally for maintenance or exploration, but it's not freedom. It's a dangerous excursion that you're glad to return from. It's a diminished existence. Safer than being dead, certainly. Better than extinction, but so constrained, so limited, so fundamentally different from what it means to be human on a living planet. This is what we'd be reduced to without atmosphere. Small populations in sealed habitats, struggling to maintain systems, living artificially, cut off from any natural environment. Not extinct, but not really living freely either. And this is what makes the atmosphere so precious. It's the difference between freedom and confinement, between a planet-wide biosphere and a sealed box, between walking outside and being sealed inside, between breathing freely and depending on machines for every breath. We have that freedom now. The atmosphere gives it to us, every day, every breath, every moment, without us having to think about it, maintain it, or engineer it. It just works. Take a breath. Feel how easy it is, how natural, how free it is. You're not in a habitat. You're not depending on life support systems. You're not monitoring air quality or worrying about seal integrity. You're just living, naturally, freely, the way humans evolved to live. That's what atmosphere provides. That's the gift we'd lose. We've spent most of this journey exploring loss. What would happen if the atmosphere disappeared? How Earth would change? how the surface would become hostile, what survival would require. Now let's shift perspective. Let's talk about appreciation, about understanding what we have by imagining its absence. Because here's the strange truth about the atmosphere. We never think about it. It's invisible. It's always there. We take roughly 20,000 breaths per day, and we don't consciously notice any of them unless something goes wrong. The air just works quietly, reliably, perfectly, without requiring our attention or maintenance or gratitude. Until you imagine it gone, then suddenly you notice. Then suddenly it becomes visible through its absence. That's what thought experiments do. They make the invisible visible. They help us see what we normally take for granted. So let's think about what the atmosphere actually gives us, moment by moment, day by day, year after year. First, obviously, there's breath, oxygen, the basis of metabolism, of life itself. You breathe in, oxygen enters your lungs through hundreds of millions of tiny alveoli, diffuses into your bloodstream, binds to hemoglobin, gets carried to every cell in your body. Those cells use oxygen to metabolize glucose, releasing the energy that powers everything you do, every thought, every movement, every heartbeat. Even sleeping requires oxygen. Even dreaming requires breath. You do this about 15 times per minute, all day, all night, your entire life. And you don't think about it unless something goes wrong, unless you're out of breath from exercise, or sick with congestion, or at high altitude where air is thinner. Otherwise, breathing is automatic, unconscious, invisible. The atmosphere provides that oxygen continuously, reliably, for free. You don't have to make it, you don't have to pay for it, you don't have to maintain systems to generate it or purify it or deliver it. It's just there. 21% of the air around you. All the time. Breathe in. There it is. We explored what happens when that's gone. 15 seconds of consciousness, maybe 10. Then darkness, then death. The atmosphere protects you from that fate. Every moment, every breath, 20,000 times a day. You're alive right now because of air. Second, there's pressure. 14.7 pounds per square inch pressing on your body from all directions. It sounds oppressive when you describe it that way, like the weight of the world pushing down on you. But it's not. It's comfortable. It's what your body is designed for. It's what you've lived with since birth, what your ancestors lived with for millions of years of evolution. Your tissues are full of dissolved gases at equilibrium with that pressure. Your lungs expand and contract against that pressure. Your blood circulates under that pressure. Your cells function at that pressure. Everything about your physiology assumes that pressure will be there. Take it away, and your body doesn't work right anymore. Water in your tissues wants to boil. Dissolved gases want to come out of solution, forming bubbles in your bloodstream. Your lungs can't function. There's nothing to breathe against. No pressure differential to drive gas exchange. The atmosphere provides the pressure that keeps your body chemistry stable, keeps water liquid at body temperature, keeps everything working as it should. Third, there's temperature regulation. The atmosphere is a system for distributing heat. Warm air rises, carrying heat from the surface upward. Cool air sinks, bringing cooler temperatures down. Winds blow from high pressure to low pressure, carrying warmth from the equator toward the poles, moving heat from the day side to the night side. Convection currents circulate heat through the troposphere. The greenhouse effect, which gets attention because we're changing it, keeps the planet about 60 degrees Fahrenheit warmer than it would be otherwise. Without any greenhouse gases, Earth's average temperature would be around 0 degrees Fahrenheit instead of 59 degrees. We'd be frozen. Without atmosphere at all, temperature would depend only on whether the sun is shining on you at that exact moment. Hundreds of degrees in sunlight. hundreds below zero in shade. No gradual transitions, no temperate zones, just extreme heat or extreme cold. The atmosphere moderates this. It makes temperature gradual, manageable, survivable. You can walk from sunlight to shade without dying. You can live in shadow without freezing. You can live in sunshine without cooking. That's the atmosphere working for you. Fourth, there's protection. Multiple forms of protection, actually, all provided by different aspects of the atmosphere. Protection from UV radiation. The ozone layer, that thin concentration of O3 molecules in the stratosphere, absorbs most ultraviolet light from the sun. UV damages DNA. It causes skin cancer, cataracts, immune system suppression. A little bit gives you a tan or a sunburn. A lot would be lethal over time. The ozone layer has been quietly protecting all surface life for hundreds of millions of years. Protection from cosmic rays, high-energy particles from space, from distant supernovae and other violent events. These particles can damage cells, increase cancer risk, harm your body in various ways. The atmosphere absorbs most of them. The magnetic field deflects many more. Together, they keep radiation exposure to manageable levels. Protection from meteorites. Every day, about 100 tons of space debris enters Earth's atmosphere. Dust, pebbles, rocks, occasionally something larger. Most of it burns up from friction with air molecules. You see the larger pieces as shooting stars, beautiful, harmless streaks of light. Without atmosphere, all of it would hit the ground. The atmosphere is your meteor shield, working constantly, burning up debris before it can harm you. Fifth, there's weather, rain, snow, clouds, wind. These might seem like inconveniences sometimes. Getting rained on when you forgot your umbrella, shoveling snow from the driveway, wind messing up your hair or blowing papers around. But they're essential, absolutely essential. Weather distributes water across the planet. Rain fills rivers and lakes, snow accumulates in mountains and melts in spring, feeding rivers. Clouds shade regions and reflect sunlight. Winds carry moisture from oceans to continents. The entire water cycle depends on atmosphere, evaporation, clouds, precipitation, runoff back to the ocean. Without atmosphere, there's no weather. No rain means no rivers, no lakes getting replenished, no groundwater, no water for crops or drinking. The water cycle collapses. Agriculture becomes impossible. The surface becomes uninhabitable. The atmosphere doesn't just create weather, it creates the entire system that makes complex life on the surface possible. Sixth, there's sound. This might seem less important than breath or protection, but consider what life would be like without it. You hear things because air carries sound waves. Vibrations in the air hit your eardrums. Your brain interprets those vibrations as sound. Music, voices, laughter, birds singing, wind in trees, ocean waves, rain on windows, thunder, footsteps, the rustling of leaves, the barking of dogs, the sounds of traffic, of people, of life happening around you. All of it requires air to reach your ears. Without atmosphere, complete silence. Perfect, absolute, eternal silence. You could watch someone shouting right next to you and hear nothing. You could stand next to crashing waves and hear nothing. You could watch a thunderstorm and hear nothing. The universe would be utterly, completely silent. The atmosphere gives you the gift of sound. Every sound you've ever heard was delivered to you by air. Seventh, there's the sky. The blue sky during the day. That's air molecules scattering sunlight, scattering blue wavelengths more than red wavelengths. The red sunset. That's sunlight passing through more atmosphere at an angle. Most of the blue scattered away, leaving the reds and oranges. The clouds, water vapor and ice crystals suspended in air. The aurora, charged particles from the sun, exciting atmospheric molecules. The rainbow, sunlight refracted through water droplets in the atmosphere. All of these phenomena, all this beauty requires atmosphere. Without it, the sky is black even during the day. Stars visible in daytime because there's no air to scatter the light. No blue, no sunset colours, no clouds, no aurora, no rainbows, just black space and a harsh white sun. The atmosphere paints the sky for you. Every day, every sunset. You rarely think about it, but it's there, creating beauty. Eighth, and perhaps least obvious, but still important, there's the feeling of it, the sensory experience of living in atmosphere. The breeze on your face, the wind in your hair, the sensation of humidity on a summer day or dryness in winter, the smell of rain approaching, that distinctive petrichor smell of rain hitting dry earth, the smell of the ocean carried by sea breeze, the feel of cold air on your skin when you step outside in winter, warm air in summer. That perfect temperature where you don't notice temperature at all because it's exactly comfortable. These sensations connect you to your environment. They tell you about the weather, about what's happening around you. They're part of being alive and aware. The atmosphere provides all of these sensory experiences. Every time you feel wind, you're feeling atmosphere in motion. Every time you smell something, you're detecting molecules carried to you by air. So that's what we have: breath, pressure, temperature regulation, protection from radiation and meteorites, weather and the water cycle, sound, beauty, sensory experience. The atmosphere does all of this, continuously, reliably, for free, without asking anything in return, without needing maintenance or payment or even acknowledgement. And we never think about it. Why? Because it works perfectly. Because it's always been there, your entire life, your species' entire history. Because we evolved in it, so it feels normal, natural, default. It's the baseline condition of existence. We only notice things when they're absent or when they go wrong. As long as the atmosphere keeps working, and it will, we won't think about it. But here's what this journey has hopefully shown you. The atmosphere isn't default. It's not a given. It's not something every planet has. It's a specific condition that Earth happens to have, and that Mars lost billions of years ago. It's a thin layer of gas held down by gravity and protected by a magnetic field. It's fragile in cosmic terms, even though it's robust and stable in practical terms. And it makes everything possible, everything. Without it, Earth becomes Mars, a dead rock, airless, silent, cold, barren, hostile to all surface life. Beautiful in its own stark way, perhaps, but not a place where humans can walk freely. Not a place where life can exist on the surface. Not a place where you can breathe. With it, Earth is this, the world you know, the world you live in, the world where you can step outside without a second thought, where you can breathe without thinking, where there's weather and sound and blue sky and clouds and all the complexity of the biosphere. The world where life not only exists, but thrives in extraordinary diversity, where forests grow and oceans teem with life, and billions of species have evolved over billions of years. The difference between those two states, living world and dead world, is atmosphere, that invisible ocean, that thin skin of air we never think about. 60 miles deep, which sounds like a lot until you remember that Earth's diameter is about 8,000 miles. It's proportionally thinner than the skin on an apple, and yet it makes all the difference. So how do we appreciate something invisible? Something we can't see, can barely feel, that works so perfectly we never notice it? By understanding, by learning what it does, by studying the science of pressure and temperature and ozone and atmospheric chemistry, by imagining what would happen without it, by making the invisible visible through thought experiments like the one we've been exploring. You can't see air, but you can understand it. You can learn about atmospheric pressure, about the greenhouse effect, about ozone and UV protection and the water cycle. You can study Mars and understand what a planet without atmosphere becomes. You can imagine Earth without air and understand what we'd lose. And then, having understood, you can appreciate. Not in a dramatic way. You don't need to fall to your knees every morning and thank the atmosphere for existing. That would be excessive and your neighbours might worry. But in a quiet way, a noticing way, a mindful way. Notice your next breath. Really notice it. Feel the air enter your lungs. Feel your chest expand. Feel the oxygen reaching your blood. Notice how easy it is, how natural, how the air is just there, ready for you, always has been, always will be. Notice the breeze on your face the next time you step outside. That's atmosphere in motion, that's wind. Feel it, appreciate it. You can feel it because you have atmosphere. Notice the sound of wind or traffic or voices. That's air carrying vibrations to your ears. All sound requires air. Listen. Appreciate the fact that you can hear. Notice the blue sky on a clear day. That's atmospheric scattering of sunlight. That blue is air making visible light beautiful. Look up. Appreciate it. Notice that you can walk outside without a spacesuit, without life support, without any technology at all. Just walk outside and breathe. That's freedom. That's the gift of atmosphere. The invisible ocean that makes everything possible. Tomorrow, the atmosphere will still be there, still doing its job, still protecting you, still providing breath and pressure and protection and beauty. It's been there for over 4 billion years. It will be there for billions more. It's not going anywhere. You're safe. But now you know what it's doing. Now you understand the gift. Now you can appreciate the invisible. And maybe, just maybe, that appreciation changes how you see the world, how you value what you have, how you think about this planet we live on, how grateful you are for the simple act of breathing. So we've explored the science of atmosphere, what it is, what it does, what would happen without it, how to appreciate it. Now let's look at something different, the stories we tell about air, the cultural understanding, the metaphors and meanings humans have attached to breath and wind and sky throughout history and across cultures. Because humans have always known that air is important, even before we understood what it was. Long before anyone discovered oxygen or understood atmospheric pressure, ancient cultures recognized breath as essential. They just didn't know why. They didn't have the science, but they had the observation, and the observation was correct. The ancient Greeks, for instance, thought air was one of the 4 fundamental elements: fire, water, earth, air. Everything in the world was made of combinations of these 4 things in different proportions. They were wrong about the details. Air isn't an element in the chemical sense. It's a mixture of elements. But they were right that air was fundamental. Different from water, different from earth, but equally essential. You can't live without it. That much was obvious even thousands of years ago. In many ancient languages and cultures, the word for breath and the word for spirit are the same or closely related. This is fascinating from a linguistic and cultural perspective because it shows how deeply humans have always associated breath with life itself, with the essence of being alive. In Hebrew, ruach means both wind and spirit. When the Bible talks about the Spirit of God, it's using the same word that means wind or breath. In Sanskrit, Prana means both breath and life force. It's the vital energy that sustains life. In Greek, pneuma means breath, wind, and spirit all at once. In Latin, spiritus means breath and soul. The Holy Spirit and respiration share the same linguistic root. This isn't coincidence. This isn't random. Breath is life. When you're alive, you breathe. When you stop breathing, you die. This was the most obvious correlation in the world to ancient peoples. They watched people die, and one of the most noticeable things was that the breathing stopped. The chest stopped moving. No more breath. And shortly after, no more life. So they concluded that breath and life were connected in some fundamental, perhaps mystical way. They conflated breath with the essence of life itself, the soul, the spirit, the vital force, whatever they call that ineffable quality that makes something alive rather than dead. Our language today is still full of breath, even though most of us don't consciously notice the connection. Inspiration literally means breathing in. When you inspire someone, you're breathing life or ideas or energy into them. Expiration means breathing out, and also dying, because when you expire, when you die, you breathe out for the last time and don't breathe back in. Respiration is breathing. Aspiration is breathing towards something, reaching for something. Conspire literally means to breathe together. Conspirators breathe together, plot together, share breath and secrets. There's something intimate about breathing the same air, apparently, at least linguistically. We say someone caught their breath, or had their breath taken away, or breathed a sigh of relief. We say someone breathed life into a project or an idea. We talk about a breath of fresh air when something new and good arrives, when there's change for the better. We describe someone dying as breathing their last. Metaphorically, linguistically, we understand breath as essential, as life-giving, as renewal, as the marker between living and dead. Wind appears prominently in stories across cultures, and it makes sense, doesn't it? Wind is air in motion, invisible but powerful. You can't see it, but you can feel it. It can be gentle or violent. It can help you or harm you. It's mysterious in a way that water or earth or fire aren't, because you can't see it. In many creation myths, wind or breath is what animates the first humans. In Genesis, God forms Adam from dust and then breathes life into him. The divine breath transforms dead matter into living being. In other cultures, similar stories, breath or wind as the animating force, the thing that makes the difference between a shaped corpse and a living person. Wind gods appear in many mythologies precisely because wind was important and mysterious. Aeolus in Greek mythology was the keeper of the winds, literally kept them in a bag and could release them or hold them back. Sailors would pray to him for favourable winds. Vayu in Hindu mythology is the god of wind and breath, associated with life force and vitality. Fujin in Japanese mythology is the wind god, often depicted carrying a large bag of winds. These deities controlled something invisible but powerful. Wind could fill your sails and speed your journey, or it could capsize your ship. Wind could bring rain to your crops, or it could destroy them with storms. Wind was respected and sometimes feared. It was powerful and unpredictable. So of course people imagined gods controlling it. The sky has always been sacred in human cultures. The dome above us, the heavens, the place where gods supposedly lived. Looking up was looking toward the divine, toward whatever powers controlled the world. The sky was unreachable for most of human history. You couldn't touch it, couldn't go there. It was the realm of the gods, of birds, of clouds, of mystery and transcendence. Different cultures had different sky gods. Zeus in Greece, hurling lightning from the clouds, Jupiter in Rome, same concept with a different name. Anu in Mesopotamian mythology, the supreme sky god. Horus in Egypt, often depicted as a falcon or with a falcon's head, associated with the sky. The sky represented power, distance, transcendence. It was above earthly concerns, literally and metaphorically. We still use sky and clouds metaphorically all the time. Sky's the limit means unlimited possibility. You can go as high as you want, no ceiling. Head in the clouds means dreaming, not paying attention to practical reality, existing in imagination rather than fact. Cloud 9 means extreme happiness, floating above the mundane world. We associate sky and clouds with freedom, with imagination, with transcendence, with things beyond the ordinary. Then science came along and explained what air actually is. Not a fundamental element, but a mixture of gases, mostly nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, and traces of other gases. The ancient Greeks were wrong about the 4 elements. Fire isn't an element, water is a compound, earth is thousands of different substances. But their observation that air was important? That was absolutely right. They just didn't have the tools to understand why. The scientific revolution demystified air in many ways. It's not spirit, it's not divine breath, it's molecules, nitrogen molecules, oxygen molecules, bouncing around, colliding with each other and with surfaces, creating pressure, absorbing and emitting radiation. We can measure it, weigh it, analyze its composition, break it down into its components. In the 1770s, scientists figured out that air is a mixture, not a pure substance. Joseph Priestley discovered oxygen. He called it dephlogisticated air, which is a wonderfully Baroque name that didn't stick. Antoine Lavoisier understood the role of oxygen in combustion and respiration. He realized that breathing isn't magic or mystical, it's chemistry. Your body uses oxygen from air to oxidize glucose, releasing energy. It's a chemical reaction, same basic principles as burning wood, just slower and more controlled. No mystery, just chemistry. This demystification continued through the centuries. Scientists figured out atmospheric pressure, Evangelista Torricelli with his mercury barometer, temperature and heat, the gas laws, convection currents, weather patterns, the water cycle, cloud formation, all of it reduced to physics and chemistry. No gods required, no spirits, no mystical life force, just molecules following physical laws, which we can describe with equations and predict with models. But here's something interesting, something important. Understanding the science doesn't make air less important. It actually makes it more impressive, more worthy of wonder, because now we know exactly what air does. We understand the mechanisms in detail, and the mechanisms are intricate and beautiful and essential. Science doesn't diminish wonder, it clarifies it, it deepens it. When you understand how the ozone layer absorbs UV radiation, that specific wavelength of light are absorbed by specific molecular bonds in O3 molecules, that's not less magical. It's more impressive because it's real, because it actually works, because the universe actually operates this way. When you know the physics of why the sky is blue, Rayleigh scattering, wavelength-dependent scattering, the relationship between particle size and scattered wavelength, that doesn't make sunsets less beautiful. It makes them more beautiful because you understand the why. When you grasp how atmospheric pressure keeps water liquid, how temperature and pressure interact to define phase changes, how the entire water cycle depends on this, that's not disappointing knowledge. That's awe-inspiring. The fact that it all works, that it's been working for billions of years, that life evolved within these exact parameters and depends on them, that's profound. Modern stories about air often take the form of science fiction. Stories about losing air, finding air, creating air, surviving without air. These resonate with us because we understand what we'd lose. Total Recall. The movie has that scene where Mars briefly loses air pressure and people are exposed to vacuum. It's dramatic and memorable precisely because we understand the stakes. Vacuum is death. The Expanse, the series, shows people living in space habitats with artificial atmosphere, sealed environments where air is manufactured and recycled. It makes you appreciate natural atmosphere. The Martian shows an astronaut stranded on Mars, having to create air and water through chemistry. It's tense because we know he needs both to survive. These stories work because we have the science now. We understand what air is, what it does, what happens without it. The stories are speculative fiction, but they're grounded in real physics. They extrapolate from what we know, and they remind us often of what we have here on Earth that we take for granted. We have real experience now with living without atmosphere, or rather, living in protected bubbles within vacuum. Astronauts, cosmonauts, taikonauts, people who've actually done this. They know what it's like to depend entirely on technology for every breath. They know the feeling of being one suit failure away from vacuum. They appreciate atmosphere in a way most of us don't, because they've lived without it. Chris Hadfield, the Canadian astronaut, has talked about this, about doing a spacewalk and being intensely aware that between you and death is a layer of material a few millimeters thick, about the care you take with every movement because you're in an environment that's instantly lethal if anything goes wrong, about coming back inside the space station and breathing air that didn't have to be manufactured, filtered, and delivered through a hose, though of course ISS air is still artificial, still manufactured, but at least there's more of it. And then coming back to Earth and breathing actual Earth air, natural air, free air, air that's been there for billions of years and will be there for billions more, air you don't have to make or maintain. Just breathe, that's all, just breathe. Astronauts often come back from space changed, more environmentally conscious, more aware of Earth's fragility. They've seen it from orbit, that thin blue line of atmosphere around the planet, that impossibly thin layer between life and vacuum. They've seen how small it is, how finite Earth looks from space. They've lived for months breathing artificial air, drinking recycled water, living in a sealed can. They appreciate the real thing in a way the rest of us mostly don't. The overview effect, they call it. When you see Earth from space, you understand its fragility in a visceral way. That thin atmosphere, that small blue sphere, that's it, that's home, that's all we have, and it's precious. The metaphors persist even as we understand the science. We still talk about breath and life. We still say wind represents change, winds of change, political winds shifting. We still look at the sky and feel something, awe perhaps, or peace, or wonder, or a sense of the infinite. Understanding that the sky is scattered light doesn't make a sunset less beautiful. Knowing that wind is air flowing from high pressure to low pressure doesn't make it feel less alive when it touches your face. Science explains mechanism but doesn't remove meaning. Both can coexist. We are breath-based life. That's not metaphor. That's biology. Every cell in your body needs oxygen for cellular respiration. You stop breathing, oxygen stops reaching your cells, cellular respiration stops, and you die. This simple biological fact underlies all the spiritual and metaphorical associations with breath throughout human history. The ancients were right. Breath is life. They just didn't know the biochemistry, the details of ATP synthesis and electron transport chains. But the fundamental observation was correct. and we live in atmosphere. We swim in it like fish swim in water, except we're so adapted to it that we don't notice we're swimming. We don't feel the pressure. We don't think about the oxygen. We just are, existing in this invisible ocean that makes our kind of life possible. The stories we tell about air, ancient, modern, scientific, cultural, all reflect this deep understanding. Ancient stories made air sacred because it was essential and mysterious. Modern stories explore what we'd lose without it, because we understand exactly what it does, and we can imagine its absence. Both kinds of stories are really about the same thing, recognizing that air matters, that breath is life, that atmosphere is the difference between a living world and a dead one. So take a breath right now. You're participating in something ancient, something that every human who's ever lived has done, something that connects you to the air, to the planet, to the 4 billion years of life on Earth. You're part of an unbroken chain of breathing organisms, stretching back to the first bacteria that learned to use oxygen. Science can tell you how breathing works, the biochemistry, the physics, the molecular mechanisms. Culture can tell you why it matters, the meaning, the metaphor, the human significance. Both are true. Both are valuable. Both help us understand and appreciate this invisible ocean we swim in. And so we reach the end of this journey through the impossible. We imagined the atmosphere vanishing, walked through those first terrible seconds, watched Earth transform into a barren rock. We explored what survival would require, looked at Mars as a warning, thought about what makes our world livable. But here's what we return to. The atmosphere is still here. Right now, as you listen to this, 60 miles of air surround you, invisible but essential, protective but taken for granted. The same atmosphere that's been here for billions of years, the same one that will be here tomorrow and all the tomorrows after. The atmosphere isn't going anywhere. Planets don't suddenly lose their air. Held down by gravity, protected by the magnetic field, the invisible ocean remains stable. Will remain stable for billions of years more. You're safe. Earth is safe. The shield that stands between us and the void continues its work, unchanged by our imagining its absence. We explored loss to understand value. We imagined suffocation to appreciate breath. We contemplated silence to cherish sound. We envisioned barren rock to treasure blue sky. And now, perhaps, you notice differently. Perhaps you feel the air on your skin with new awareness. Perhaps your next breath feels less automatic, more gift. If you've enjoyed this exploration of the invisible ocean we swim in, if these quiet contemplations resonate with you, I'd be grateful if you'd subscribe to the Sleepy Astronomer. There are more cosmic questions to explore, more ways to understand what makes our world extraordinary by imagining worlds without these gifts. And if this journey meant something to you, a gentle like helps others find their way to these late-night wanderings through space and science. Thank you for traveling with me tonight, for imagining the impossible, for being curious about the invisible forces that make life possible. Sleep well, surrounded by your invisible ocean. Dream of silent voids if you like. They make for interesting dreams. But wake to the reality we're blessed with, a stable atmosphere on a living planet, protecting you from the void, giving you breath and sound and weather and life. Good night from the Sleepy Astronomer. May your dreams be peaceful, and may you wake to the gift of air, just as every human who has ever lived has woken to that same gift, that same protection, that same invisible embrace. Until we meet again, breathing easy in the ocean of air,